आपका आपका नहीं सर का वीडियो ऑडियो ऑन नहीं है.
Srivastava sir, it's about to 10, only 1 minute is left. So I have done this live streaming and started recording as well. Srivastava sir, you are on mute. Sir, you are on mute.
Yeah.
Yes, sir. So may I start the session?
Yeah, please.
Okay. I request all the distinguished members present over here for the beginning of the formal session of day 2 of 8th annual convention of IAPTRC1 kindly mute their mics so that we can begin with the session. Once a great man said, the cure for boredom is curiosity. There is no cure for curiosity. The more you learn, the more you want to learn, the more the world becomes more interesting to you. And discovery, it becomes more fun. With this, very marvelous, very charming, very blessed, and a very good morning to all the eminent speakers and participants present here. Myself, Poonam Jain, again your host for the day, would like to welcome you all on day 2 of the 8th annual convention of Indian Association of Physics Teacher Regional Council 1 on the theme Rethinking Physics Education in the context of National Education Policy 2020. I am happy to inform you that this session is being recorded and streaming live on YouTube and Facebook of IAPTRC1. The link for the same will be shared in a while in the chat box as well as via mail. There is an announcement for the speakers of the day that time allotted for the invited talks are 25 minutes followed by 5 minutes for question and answer session. And there is an announcement for the paper presenters. The time allotted for the paper presentation is 12 minutes followed by 3 minutes for the question and answer. So I request everyone to kindly adhere the time and kindly wind up your talks within the given allotted time. Without further ado, I would like to invite our first speaker, Dr. Samrendra Pratap Singh. He is an associate professor in Department of Physics, Shiv Nadar University, Gautam Budh Nagar, Uttar Pradesh. He is going to speak on the topic a research-centric 4-year physics undergraduate curriculum at Shiv Nadar University for fostering diverse scientific skill. I welcome you, sir.
Thank you very much. Am I audible?
Yes, sir.
And I hope all of you are seeing my slides.
No, sir. Slides are not visible right now.
Oh, is it?
So kindly share it once again.
Now?
Yes, sir. It is coming. Yes, sir. Kindly go to the presentation mode.
Okay. I hope all set.
Yes, sir. Yes, sir. Perfectly fine.
Okay.
Thank
Great.
you so much.
Thanks. Okay. Very warm good morning to everyone. And myself, Samrendra. Today I'm going to talk on a research-centric 4-year physics curriculum at Srinagar University for fostering diverse scientific skills. Today I'm presenting on behalf of Department of Physics, Srinagar University. And first of all, I would like to thank IAPT RC1 unit for giving us this opportunity for sharing what we have been doing over last 8 to 9 years at Srinagar University, what we have been practicing. And special thanks to Professor Srivastava for extending his invitation to us. So let me begin with the quotation that in the quest of nature's truth through learning and applying fundamental laws of physics, which all of us doing, I'm just going to share some of our experiences which we have been practicing and the kind of input or the feedback we get from students. I'll be sharing in next couple of minutes with you. And please feel free to put up questions which you have towards end of this talk. So for beginning, just to set agenda for my talk, I'll quickly refresh some of revolutionary changes which physics have given us over last, during 20th century. So first couple of decades have witnessed the special and general theory of relativity and evolution of quantum mechanics. And since 1947, since the discovery of transistor in 1947, we have witnessed that our world got changed, and what we are seeing around us, the digital era, it's all started from there slowly. We can see as a consequence application of quantum mechanics, uh, discovery of transistors, LEDs, memory devices, entire solid state electronics have revolutionized our life around us. And so a couple of other changes which we see and which we are witnessing in current generation. Uh, if I talk about 21st century, in 21st century, first 2 decades have seen some of predictions and discoveries. I especially would like to highlight around the physics in an interdisciplinary world, where we see that we all know that nature is unified, and we just need to develop our approach for understanding, for explaining the phenomena around us, and for developing solutions for the challenges which human civilization is facing in current day. So definitely physics is an integral part of interdisciplinary problem system, which we are seeing around us. And some of examples which we can see the challenges of climate change and of social progress. And we are seeing a lot of problems which are coming of us, from our society, and solution need to be proposed where physics methods and approaches going to play a very significant role in offering solutions. And that's where um, we have to pitch to train our undergrad students, which should be able to take on the challenges and prepare themselves for taking the challenges and finding solutions. So physicists play a crucial role in generating solutions to the real world problems. And as yesterday the speakers had also talked about, Professor Rupa Manjari Ghosh, he had also pointed out about disruptive technologies, artificial intelligence, Internet of Things, and machine learning, revolutionizing the era of creativity and scientific motivation. Today, in current date, entire world is facing a pandemic problem, and here also we can see that a lot of solutions are coming from a lot of solutions which people are trying to provide, largely coming from physics, involvement of physics, direct dependence we can see. So here I would like to highlight of articles which had come out recently. Artificial intelligence enabled rapid diagnosis of patient with COVID-19, and this research is very much linked with the kind of contribution from physicists we are seeing in this for finding this solution. So scientists are employing X-ray, electrons, and neutrons to decipher and disable the molecular machinery of novel coronavirus. So single crystal X-ray, we have seen physicists have been doing for studying structural microbiology and finding out the structure of single crystals. That technology is very much being used for studies even in the current date for finding a rapid diagnosis or identifying the protein molecules which are around us, which are contributing significantly for this COVID-19 disease. And a lot of effort are going on this side. And we can see that the role of physicists are very crucial in understanding and finding out solution for this problem as well. However, there are challenges which we see due to, the kind of disruptive technology we are talking about, or kind of changes we are seeing for providing the solutions. Major challenges are going to be handling of big data, managing of homogeneous energy cost of computing. And even here, the role of physicist is very important. And that's where we have to prepare ourselves, keeping our fundamentals intact and finding out finding out solution in the context of interdisciplinary nature of challenges. So out of all this, which we can see here, the major challenge which coming out, the size of digital universe, which is going to be around 44 zettabytes, demands a significant higher density of computing as well as the data storage, what we have today. I mean, with respect, I mean, as compared to what we have today. And even for this, the role of physicist is very important. So seeing all this interdisciplinary nature, evolution of physics, how life around us have changed, the kind of challenges human civilization is having, keeping in mind the concept of sustainable development, the relevance of physics undergraduates is going to I mean, it's going to very important, and that's where the physicist training is a very important, and I'm sure the kind of work IAPT is doing, it's a very necessary, and it becomes more challenging in coming days and more relevant for undergraduate training. So with this background, I would like to talk about what kind of training programs or what kind of UG programs we have. In India, we know that traditionally we offer, we see the first 2 year undergrad students, they do they do a couple of courses, a couple of subjects around the major, which is of course physics. And third year, they tend towards a specialization in physics. So this is a typical most of universities in India offering. And here the undergraduate degree is very important. It plays a very crucial role in developing students' conceptual understanding of fundamental of physics. So we can see that the foundation developed during undergrad student during their undergraduate degree, that's some sort of foundation which is going to play a crucial role for budding physicists. And on that foundation, whatever they are going to opt for future career, that's going to largely depend on. And that's where we have to play a crucial role for training and for motivating them for learning things in current context. As Professor Ghosh yesterday pointed out that training undergraduate students, we have to keep in mind that students need to be trained such that they should not be just relying on the concept, whatever they have memorized or whatever they are practicing. They should be able to find out, they should be able to define problems, they should be able to find out solution for the given challenge. And that will require training of brain, and that's a very important task which has to be done. So I'll draw your attention towards this report which came out in 2016, and this report this report was presented to American Physical Society. However, it's relevant to all physicists, and that's why I'm pointing it here. And it especially talks about how, I mean, what kind of things, what kind of challenges physics teachers or physics departments all over the world they have, and how to train physics students for 21st centuries. However, these are, you can say, some sort of just guidelines, and each department, each country have their own limitation, their own definition of problems, and accordingly has to be, accordingly solution has to be provided, or methodology has to be developed. So traditionally, a successful physics career means an academic research and teaching positions. However, we know that hardly 15–20%, if I talk about the total number of undergrad students pursuing physics, almost 25%, 30% student, they choose academic career, and rest of the students, due to whatever limitation, whatever thought process they have in mind, they go to other streams. So our physics undergrad training definitely should focus, should contribute to overall career shaping of the students. So what skills, knowledge should the next generation of undergraduate physics degree holders possess to be well prepared for a diverse set of careers? As in the previous couple of slides, I tried to show you the kind of challenges we have, the kind of interdisciplinarity we have. Definitely, it requires training for diverse set of careers, and which definitely is very relevant in current day. So further, this report recommends what's expected from physics undergrad students. So we can see that physics specific knowledge, that's a very important. And whenever we are saying that interdisciplinary training or interdisciplinary has to be integrated in physics undergrad training, it doesn't mean that we have to anywhere compromise with the fundamentals. Fundamentals has to be intact, because remember that I mean these fundamentals are going to be a foundation for students' thought process or students' training, which in future he or she is going to demonstrate. So it talks about physics specific knowledge and scientific technical skills, communication skill, professional and workplace skills. Almost all the departments, all the faculty members, they do these things, and it never, you can say, some sort of highlighted in such a specific manner. But the best part of this, qualitatively, these reports are helping us to find out, you can say, stream-wise integration and putting some components which serve the purpose of developing such skills in students. And that's where I think our new education policy also talks about, the kind of training, the kind of skill development we are talking about for the future workforce, that will be very much relevant and necessary for growing future workforce. So these are the kind of expectation from world around us. There are few strategies, few solutions, but we know that there could be multiple solutions to this problem. And some of the steps recommended by this report, by the panel in this report, and they ask for emphasis on standard courses, infuse career-relevant technical skills, laboratory courses, incorporate communication and professional skills. So they have suggested some of things to do, or some of the things to integrate in our in physics undergrad curriculum. But as I said, that there could be multiple solutions. So what we feel, one of the solutions could be, if you look on the most of the components, most of the recommendations are the kind of skills in demand. We feel that by integrating research, a lot of things can be incorporated, and the result could be very much beneficial for students, and the result going to be manifold in the sense of developing the required skills. Apart from that, training undergrad students for future research career, which is going to be just at the very beginning of their undergrad training. And it's very relevant, the kind of changes we are seeing around us. If we compare life in India 25 years before, then we know that the kind of challenges we had, like even to find a paper, we had to go to library, search for journal, go to Xerox machine, copy it, and then read it. The kind of challenges we had at that point of time. Nowadays, even if I have to find a reference, just on one click, paper is going to be there, and reading task, reading, grasping, discussing the further course of action that can be decided immediately. So the kind of time saving students, the kind of technology we have around us, it also motivates us to bring such changes in our curriculum, so that students should feel part of their training with the kind of technology available around. So for preparing tomorrow's trained workforce, the physics undergraduate programs need to focus around these. So prospect of 4-year physics UG programs. As I say that the integration of research is going to be, it could be one solution for developing such skills in students. We need to keep in mind that for doing all this, we need some flexibility in our curriculum, and probably the 4-year physics undergrad program could be one way for doing such kind of rejigging on our undergrad curriculum. So in SNU, we have been doing over last couple of years, as Professor Ghosh yesterday pointed out, that we are very new. I mean, just 8 years we have completed, at least in the context of Department of Physics, because we had started our program somewhere in 2012. So students of research intensive universities are not just trained academic minds, they are assets for potential employers and the economy. This is a report from International Alliance of Research Universities. And they find that students which have exposure to research at undergrad, they have better capability to solve problems, and they have instrumentation competency, software competency, and coding competency. So these kind of things which are desired, expected from undergrad program, which these are already available if we integrate research in undergrad curriculum. So now I would like to give a quick overview of physics research program at Srinagar University. So it's centered around the core and elective courses, major and minor. So primarily I'm talking about major. And these curriculum are designed to have different components. That's having CCC course, and CCC courses, these are common, core common curriculum. These are the courses where students have to, there are defined 8 categories, and the courses are developed for all these 8 categories, and the student have to pick courses. And this is the thing at the beginning of UG program at Srinagar University. It was, it says that all the programs has to be 4 years, and our founding Vice Chancellor, Professor Nikhil Sinha and Professor Ghosh, they come up with the proposal of having core common curriculum. And these are courses common to all undergrad programs at Srinagar University. Means students have to take, irrespective of their major, they have to do core common curriculum, university-wide elective. And these two must have 42 credits, which is a significant part of their total number of credits for degree. And for BSc 4-year program, we have final year, as name suggests, that BSc Research in Physics program. So that's having an undergraduate thesis. That's a final year, totally devoted to research. And student, they do undergrad thesis. And internship during summer or winter breaks. Of course, winter breaks are shorter. We encourage students to go for internship, and the students contact faculty members outside SNU to other institutions, and they work under them. Teaching laboratories, that's a very important part of undergrad program at physics department at Srinagar University, which I'll elaborate a little later. And the opportunity of undergraduate research, that's also, you can say, some sort of very important opportunity or scheme for undergrad students, inculcating research in at a very early stage in our undergraduate students. So this gives the overview of our UG program. And specifically, if I talk about undergrad program, it starts from admission process. Our admission process, we have SNU SAT, that's online test, and it's also having physics, it's having a subject test. We also take students from JEE percentile and SAT and ACT score, followed by interviews. So personal interview we take. This time also we have conducted personal interviews for students, and after that we select the students. Once the students are selected, they start their undergrad curriculum. And for physics, total number of credits required are 151. And as you can see that the first 2 years, we have major 54, UWE 12 and CCC 18s. And this is the foundation year, which we consider in our curriculum. So all the fundamental courses students are going to do during first 2 years. And third year is going to be advanced year, where students are going to revisit the concept developed in foundation part using sophisticated theoretical and experimental tools. And fourth year is fully devoted to research, where students will be doing a couple of major electives and their research thesis. This research thesis is 1 year, which is spread over 2 semesters. So that's a quick overview of our physics undergrad program. Now let me highlight individual components of our program. So benchmarking of physics undergraduate student, that's very important. And we have done before preparing our curriculum, we had surveyed almost all the best institutions in abroad and in India, and we developed our curriculum. I would like to highlight here contribution of Professor Vikram Vyas. He had played very crucial role in developing our curriculum. He was part of our department at first 2 years. And as we can see in the slide, the undergraduate degree program all over the world, it covers almost 140 to 180 credits and a couple of basic courses which are part of these curriculums: mechanics, thermodynamics, quantum physics, experimental laboratories, mathematics, computing, optics, electromagnetism, optional subjects. That all we have in our curriculum, and it's we can say that our program is very much benchmarked with the high rank institution in India and abroad, and it's showing a result as well, which will be which I'll be highlighting in later slides. So if I highlight the distribution of courses year-wise and semester-wise, then we can see a quick look on the kind of diversity we have in our courses. We encourage students to do courses from mathematics, chemistry,
Excuse me, sir.
and yeah.
I'm very sorry to interrupt you, but we have another 5 minutes.
Sure, sure. I'll try to wrap up within that.
Okay,
So
thank you.
I would like to highlight. I'd like to highlight here the course specifically which we have introduced at very early stage to our students, the computational physics course. This computational physics course is where I mean, in this course, students are studying Python, and once they learn, they try to solve physics problem using computational tools, and that definitely inculcate computational skill in these students at very early stage. And we keep repeating, I mean, we keep generating projects in different courses, which encourages a student to use computational tool, computational skills developed in these two courses. And at advanced stage, we have advanced experimental physics course. This course also have a little different character. And in this course, we have lab courses and weekly lecture. And this weekly lecture component, it talks about the kind of experiments they have, what's the theory behind it, what kind of experimental setup they have, and the deep understanding of experimental setup they develop through these lectures. So these kind of things we have been practicing, and that's very much rewarding for our undergrad students. Delivery of courses, most of time we do through our tutorial programs, and these tutorials are encouraging students to solve more problems. And teaching laboratory, as I said, that it's an integrated part of our curriculum. And we have teaching laboratory, which are very modular, where instruments are in component form. And we have instruments from pretty standard companies like Phoebe, and we have purchased a lot of sensors from motion sensor, force sensor, and light barriers from Bordier. And these are placed there. Students can take and build up their experimental setup as per need of their experiment. And in these laboratories, we also encourage students to develop some projects. So first 8 weeks, 10 weeks, first 8 to 10 weeks, students work on their standard experiments. And after that, 3 to 4 weeks they have for project, and students come up with their proposal, and they work on their set project using the infrastructure available in the lab, and which is definitely giving very good experimental skill to our students. And current date, where labs are not functioning, we are using PHET interactive simulation, LT-SPICE simulation, and simulator.io for doing virtual experiments. So these are a couple of images which shows our lab setup, mainly teaching laboratories. And now I would like to move to research component. As I said, that the undergrad thesis. So here in this undergrad thesis, students come up with their own proposal, and these proposals, students sometimes they discuss with the faculty members, and they draft their abstract and outline of project. Students are also contacting external supervisors on their own, defining their research problem and approaching faculty members to conduct these research. And our all research infrastructure, it's open to students. And I would like to especially highlight one case here. This student, he come up with the proposal, which none of our faculty members were working in this area. However, this fellow come up with this proposal. We worked on it, and he had very good outcome of his research thesis. And due to pandemic, his research work got affected, but I'm sure in next couple of months, he will be able to pursue his research further, and it will lead to some publications in future. Apart from that, as I said that OUR, that's another scheme which gives exposure to research to our students, and this scheme is introduced by Professor Ghosh, and it's very dear to her. She even from her busy schedule, she managed time to talk to a student, encourage them to do this research, and it has some internal funding for students, and these students come up with the proposal. After first year, a student can choose a topic. They talk to relevant faculty member, and they can work on these problems. Some of the projects which I have highlighted here, and exploratory UG research projects. This lab is developed where a student can go and work on their research ideas, and it's most of time open for students. These are the areas where research at Srinagar University taking place, where faculty members are engaged in these areas. And material research, that's one of the strong point at Srinagar University. We have developed advanced labs with the leadership of Professor Ghosh, and almost all the required instruments are there for conducting research, and our department is doing very well in the area of material research. Some of the online tools which already we have been practicing at Srinagar University, which are highlighted here, and that have given us even in the even in the days of this pandemic, we switched to online mode for teaching with the help of these already already available tools in our campus, and which have helped to continue our teaching and research very much. So students' activity is very important component of undergrad physics students, and I would like to show here some of the activities which our physics students do, and they are very active in organizing talks, inviting external speakers to campus, and which we can see from these activities. They also participate in international events, and recently we had conducted international physicist tournament where Nisar Bhubaneswar and ISER Bhopal team had participated at Srinagar University. So these are some of the teaching learning practices which we have been following at Srinagar University, which are highlighted here. And that's some sort of summarize the kind of thing I have presented earlier about our undergrad program. So success stories to continue. I would like to highlight a case of Achal Awasthi. He is a student of our first batch. So we had started our undergrad program with the 2 students. We can see how he had used the foundation of physics through undergrad program and developed multidisciplinary nature. So even while working at Srinagar University, he came up with the research proposal to work on econophysics. He wanted to use physics tools for studying share market. And after that, after completing successful undergrad program from Srinagar University, he went to Ohio State University for statistics and a master's in stats. And then currently he is pursuing PhD at Duke University in biostatics and bioinformatics. So that shows that the kind of thing we have in our curriculum, that's giving motivation to students to pursue interdisciplinary career, and that's enabling them to take on challenges what they see around. So the research which our students conduct, they generate international journal publications. So some of recent papers I have shown here. These are undergrad students who have generated while working on projects with our faculty members, and that's one of the most satisfactory and rewarding point for us. The kind of training we are giving to our undergrad students, they are responding well to our expectation. And these are some of the institutions where our students have been pursuing their higher education, higher studies. And the best part is that these students, just after a BSc, completing a BSc 4-year program from Sunada University, they are getting good opportunity in institutions abroad with fellowship, which is very difficult to get just after completing undergrad program. So that's one of, you can say, some sort of satisfaction for our program, and it's a reward for us, whatever we are contributing to building these students. So these are the faculty members of physics who are constantly working for training undergraduate students and conducting their research at Sunada University. So this is Department of Physics. And with this slide, I would like to thank my colleagues, and on behalf of them, I thank you very much, and I'm open for any questions if you have.
Thank you so much, sir. You have showcased how the faculties are using the scientific skills for the undergraduate courses, 4-year courses. Also, you have highlighted a lot of strategies which you are practicing right now at Shivnadar University. That was really amazing to hear from you. Now I request Dr. Yogesh Kumar to kindly take the questions if available in the chat box. Thank you. You are on mute, sir. Kindly unmute yourself.
So thank you, ma'am. I hope that I am audible to everyone. Thank you so much, sir, for sharing your deep knowledge on research-centric 4-year undergraduate curriculum at your institute. So there are a few questions in the chat box. Let me read. First question from Ms. Rashmi Srivastava. What specific type of communication skill is required to teach physics?
Hello. Hello, am I audible?
Yes, sir, you are perfectly audible.
Okay. Yeah, so the main point is that the physics concept should be clearly communicated to students. So the communication skill required is primarily for expressing yourself clearly in front of students. That's aim of the communication skill which is being taught, and that's where I think uh, faculty members and the teaching community need to look on.
Okay. Thank you, sir. Next question is from Mr. Hota. Compare your UG physics course with the same course offered by NICER and ICERS.
Sorry, I didn't get your question.
Yeah, so I repeat, how do you compare your UG physics course with the same course offered by NICERS and ICER?
See, as I said that the foundation level courses, physics is not going to change. So at any institute, these physics courses will be offered. It's a skill of faculty members, how they are teaching, what kind of examples they are taking up to discuss, what kind of problems they are discussing in classes. So these are things could be different. And as I said that the physics is not going to change. Physics is the same concepts are getting taught in various institutes all over the world. It's a the personal component comes only at the places where faculty members are kind of examples they take and the kind of communication they have to their students.
Okay, thank you, sir. Another question is from Anshu. Suggest some ways of motivating student at school level to take up physics subject in higher studies. Also during this pandemic period, to impart practical knowledge is difficult. Kindly suggest some ways of imparting effective practical sessions.
So for effective practical session, one thing which always will be lacking, that hands-on experience. So it's just something like seeing something on a screen and feeling like I can't touch it. So that kind of difference is always going to be there, and we have to bear with us for some time. However, for motivating students, I can definitely say that it's something like you can encourage students with the interesting examples, interesting problems, and you try to highlight the kind of physics involved there and how physics is rewarding in terms of solving complicated problems. So this could be one way to encourage students or to involve students in in their study, especially at school level. Because I mean, most of time students, they don't see where these concepts are getting used. And that's where most of students, they feel that they are lacking motivation to pursue, or they find physics becoming difficult to them. So that's where I think, I mean, this could be one way to encourage them.
Okay. So next question is from Dr. Uday Tyagi. Are the labs associated with each theory paper each year?
No, not exactly. Some of our courses are just theory course, and labs we have like first year, second in first year, first 2 years. First semester they have one lab, and that's very much around mechanics. And second semester they have a lab which is having electricity, magnetism, and electrodynamics. And in semester 3 and 4 they have electronics lab and advanced physics lab. And final year is fully, as I mentioned, that it's research for their research. So in final year, they conduct experiments in labs.
Okay. So there is no more question in the chat box. So let us thank our speaker.
Thank you.
Thank you so much, sir. Now I invite Poonam Jain ma'am to proceed further.
Thank you, sir. The next speaker for the day is Professor Vijay A. Singh. He is a visiting professor, CEBS, Mumbai. He was also ex-professor of physics, IIT Kanpur and HBCSC, TIFR, Mumbai. Today he is going to present MCQs and assessment, do's and don'ts. I welcome you, sir.
Good morning to everybody. Am I clearly audible, Poonamji?
Yes, sir, you are clearly audible.
Thank you. A very good morning to everybody, including Poonam Jainji. And a big thank you to the RC1 for asking me to give this talk. My talk is somewhat orthogonal to the previous speaker's talk. Samrendraji gave a very nice talk on undergraduate education at the Shivanadar University, and he described it very wonderfully. My talk is different, and I've got my, by the way, I've started my clock at 25 minutes, so I will stop at 25, and if I don't, please remind me. I will talk about assessment, and should I share my screen now? That might be helpful. Yeah, here it is. Let me share my screen. Okay, here it is. Okay, so is this visible to people? I mean, assessment?
Yes, sir.
Thank you. So it is about assessment. It is about setting up question papers, which are largely nowadays in India, multiple choice questions. Okay. It is also about multiple choice questions, which are used in what is called concept inventory, which is part of physics education research. So it is basically these fields that I'm addressing. And to begin with, I have to tell you that with 30 to 40 years of experience in setting one question paper after another at the national level, whether it be IIT, whether it be Kishore Vaigyanik Protsahan Yojana, whether it be NTSC, I have some experience, and some of it is what I will share with you. What I cannot share with you is because of the time constraint. I have a paper on this, which I have shared with Poonamji. I will also flash the reference in the end, and it is there as the first paper in ResearchGate. It's in Physics News 2011. Setting of a question paper, okay, should not be looked down upon, by the way. Okay, by the way, Green's theorem, which played such a central role in Maxwell's electrodynamics, was set as a problem for Maxwell by Professor Green. Okay, and it turns out that at that point in the exam, Maxwell was not able to solve that question. It made a deep impression on him, and later he went on to use that theorem very advantageously in his work. So it is a lonely profession. Setting up of a question paper and not seeing the 100,000 students in front of you is somewhat lonely. And the way a student should see a good teacher's question is that the teacher is trying to communicate with him. Okay. So let me go to the next slide to give you the idea. The state of mind of the test designer, it's a loneliness of the faculty. That's, some of you may have read the book, The Loneliness of a Long Distance Runner. Similarly, it's the loneliness of a long distance, an invisible question paper setter. It is basically trying to attempt a dialogue with a student. Okay. One has to be clear about the objectives, of course. Is the test that I'm designing, and basically now it's very clear to you, this is a talk for the teachers, and probably you have better ideas as teachers than I have. Okay, so it might be something like taking coals to Newcastle, okay, where there's already a lot of coal. We have to be clear about the test. Is it an elimination test? Is it a selection test? Am I going to select only 3,000 students, about 10 out of 10 lakh students? Is it like the NEET exam whose results are going to come out tomorrow? Okay. Then is it a speed test? Do I want to have an ability test? An ability test is an Olympiad question paper in which IIPT plays a very central role, in which 500 students from across the globe gather together to solve just 3 questions each in 5 hours. That is, so it's simply a test, not of speed, but of your creativity and ability. Okay. Is it a misconceptions test? Am I trying to test in a certain area like Newton's third law, for example? Am I trying to test whether the student has understood all the nuances of this subject? Okay, so I'm not going to hit him over the head. If he doesn't get it right, it tells me something. Say, for example, for the third law, is action and reaction, I would say, is it simultaneous? Okay, half the students might answer it is not simultaneous, because action and reaction, by their very terminology, means reaction follows action in time. Okay, which is of course wrong. But I have to see if it is a misconceptions test. I devise it like that. Is it a remedial test? Is it a test to help the students learn while he or she is taking the test? In which case, I'll make the test stepwise and all very simple. That would be a remedial test. Or is it an institutional evaluation test? It's like my class end of the semester exam that I do. Is it that kind of a test? Okay. So the tests that I will speak about are multiple choice questions, something like a misconceptions test or an institutional evaluation test. So it is not, I'm not talking about an Olympiad level test where I will set only one question and give a student the whole day to solve it. Okay, so let me continue and let me pause for one moment to ask, am I still clear or am I speaking too fast? Poonamji? Okay. I will assume that I'm in good shape. I mean, okay.
Yes, sir. Yes, sir. It is fine.
Okay, thank you. Okay, so let me continue. So how do you make the question paper? Okay, you make the question paper and there's a box here and you get the questions from books. Let us admit it. We look at the book, we look at the syllabus, we talk to our peers. For example, when you're setting a paper of, for example, of the type of the Kishore Vaigyanik Protsahan Yojana or the IIT, you have 10 other people sitting with you and you're talking to them while you're setting the question. So you have peers. You look at earlier tests. Yes, why not? It's not cheating. Look at earlier tests to see what they have asked. Okay? And then having put all of this together in a question box with question 1, 2, and 3, you have a moderation process, which has to be done honestly. Okay? And which is rarely done honestly. Okay? And then there is a pilot study. So there are two different things. I have to tell you this. Once you make a question, you have to evaluate the content of the question. That is called content validation. That you get from your peers and from somebody else who was not involved in making that test. He or she is going to look at your question and say, okay, they look all right, or I don't understand it, or what you have done is wrong. Okay, that's called content validation. Apart from that, a very important component is called face validation. The face validation is you give the test to a small group of students on the side to see if they understand what you're writing. See, sometimes what you write may be understood by an expert, but a student may simply not understand what kind of question you're asking. You have to do a pilot study if you are very serious about the test. In fact, in all misconception studies, concept inventory that we write for the American Physical Society, there's one of mine on the website over there. You have to do a pilot study. And then you have a whole bunch of checklists. So what I will tell you now in the next few slides is just review what we all do often, what we all need to do if you don't do it, about three processes. One is what is essential. Number two, what is good practices? And number three, what is a checklist that you must have? Okay, so let me continue. First of all, you have to be open about the source of your test question. If you have taken it from a book, please say so. Okay, you can say that I took it, I was inspired by a certain book, I changed it around, and this is what I've made it into. Nothing is done in vacuum. Okay, once in a while you might think of a very original question, but largely it is from a book, it is from the syllabus, or it is from another earlier exam. So you have to be open about the sources with your peers. Do not be dishonest. The second is you have to be concise. What is the point of asking this question? If you're asking a multiple choice question, you cannot go all around and tell a whole story about it. Just ask what you want to ask. Okay, say the minimum possible in asking the question. The third is you have to be precise, and perhaps a question can be helped by doing a diagram. Okay, projectile motion, two projectiles fired from two sides, they collide in air. A very simple thing to be very clear about, are they in the same plane or are they in different planes, different vertical planes? Okay, a diagram always helps. Fourth is confidentiality. Okay, it is very important that what you do is destroyed, okay, as soon as you leave the room, okay, and it is left only with the person who is in charge of conducting the exam. These are rules that you cannot flout. Okay, confidentiality, help with the diagram, being concise, and being open about your source. Okay. Good practices. What is a good practice? Having done this, what other things do you require of me? One is, it is important, it would be nice if you make the problem relevant and interesting. For example, if I'm asking a question about the center of mass, okay, instead of saying, get me the center of mass of my, what do you say? Get me the center of mass of this iPhone or something. I can say, look, the center of mass is a very important concept, say in finding an exoplanet. Here is the sun. Okay, I cannot do the animation because I'm using the PDF file. And here is a planet. When the planet is on top, okay, the sun or the star is below. I'm sorry, it's not the sun, but the star. And the center of mass, which is marked by a cross, is invariant. Similarly, if this heavy planet goes to the south here, or goes down here, this sun or the star will move to the north. Okay, so it will wobble. So if I have to explain the concept of wobble and ask a very simple question about it, okay, I'm sorry, if I have to ask a question about the center of mass, I will do something which will be relevant and from which a student or later students who see these questions will learn. They will learn about the wobble method for finding exoplanets. Or I will tell them about what was called the Fosbury flop. Mr. Fosbury in 1966 Olympics revolutionized the high jumping field by jumping backwards. He didn't jump forwards like a horse, but he jumped backwards such that his center of mass was always just below or above the pole bar over which he's jumping. So he jumps in a way that is most of his body, half his body is below the bar, half his body is above the bar, and he makes it across. Okay. So that would be an interesting question. So you have to make a question perhaps relevant and interesting. Okay. Not mandatory, but it is good practice. Okay. Also make it socially relevant. Okay. For example, we are always advised not to cross the tracks. Okay. So if I'm going to ask a question on kinematics, okay, I will ask the following question, okay, which I've done, by the way, okay, in earlier exams. The speed of a fast train is, I would say, is about 25 meters per second, tell him 90 kilometers per hour, and I'm somewhere ahead and I have tried to cross the tracks, something not advisable, and I have fallen on the tracks. Can the driver of the train, can she apply the brakes in good time so that I am saved? So I'm doing something which is socially not correct. In fact, which is legally not correct, but we do it all the time. We are crossing the tracks of a fast train approaching, okay, and we are about, say, a kilometer ahead. Will I be saved? Okay. And then you tell them that the maximum deacceleration a fast train can apply is about half a meter per second square. Half a meter per second square, imagine. Okay, if it is only half a meter per second square, okay, how long will the train travel so that it will come to a halt? And supposing I'm way ahead, say half a kilometer ahead, will my life be saved? And you ask these questions and the answer, of course, is no. Okay, even if you're 600 meters ahead of this track, you will not be saved because the maximum deacceleration is minus half meter per second square. Why is that? That is because if it applied a higher deacceleration, the whole train would go off the rails and you'd be killing about 1,000 people to save one person. Okay, they do the calculation, you can get 625. Okay, they're just like a very elementary example. And then you haven't even added the reaction time. So you add the driver's, her reaction time of 2 seconds. So it comes out to be 6 times 75 meters. If I have to ask questions, I would make it socially relevant like this. I would make it interesting by asking about the Fosbury flop. If I have to ask a question on center of mass. If I ask a question on one-dimensional kinematics, I would ask such a question. So someone learns while she is trying to answer the question. Okay. Third thing is, you must try to inspire symmetry and scaling arguments. Okay. So, for example, in a very simple example of symmetry would be the 9th standard question you ask. If a ball is going up with 9.8 meters per second, okay, what is the speed when it lands? You don't have to work out any kinematics. You use symmetry to say that the ball will have the speed of 9.8 meters per second. Okay. Take a ball, throw a rock, it goes straight up, comes down, that's all. That's a simple problem. The time it takes to go up is the time it takes to go down. The speed with which you throw up is the speed with which it comes down. These are given by symmetry arguments. Not all examples at 12th standard level, and I'm talking still at higher secondary school level or high school level, not all of them are as trivial as this, I can tell you. Okay. For example, a very famous example that students try to skip and not learn is the problem of minimum deviation of a prism. To get the angle of the minimum deviation of the prism, you have to use time reversal symmetry. If a ray is going like this, it's going to come back in the same direction. Okay. And this is a very good example of time reversal symmetry at the higher secondary school level. The problem of minimum deviation angle of a prism, for example. Okay. I can think of many more examples. For example, there is one area that I find, it is what I call as the area where the equation starts telling you lies, where the equation is not truthful. It's very useful to test students on that. Here is the example of a ball being thrown up. Okay. Right. ball. Supposing I put here, for example, the speed, of course, the initial speed I've told is 9.8 meters per second. Okay. It will go up to a height of 4.9 meters. So the ball goes up this high. But now I use this equation and I put t equal to 3 seconds. Now note, it will go up in 1 second. It will go down in 1 second. Okay. But if I put t equal to 3 over here, what will I get? I will get two solutions. One of them will give me h to be negative. Okay, it will probably, the student will interpret this. If he is not good or if she is not good, he will say that the ball is about minus 10 meters below the ground. No, that equation is not correct then. The validity of the equation is only up to this point, h equal to 0. The answer is the ball will lie on the floor. Okay. So there are times when the equation is lying to you, and every equation has a range of validity. Every equation lies to you, I can tell you that. Okay. So you have to find that range of validity and test the student on that. It's a good practice to do it. Another example is of radioactive decay. People use radioactive decay, and you say, supposing the initially I have 1,000 nuclei, okay, and the half-life is say one day. After 1 day, what will you have? How many atoms will you have? How many nuclei will you have? The standard answer would be 500. If there's 1,000 atoms to begin with, if there's 1,000 nuclei to begin with, you wait for 1 day, half-life is 1 day, you will say 500. That is wrong. This equation doesn't work if you have small number of atoms. It could be 1 atom, it could be 0 atoms, or it could be 1,000 atoms. The damn thing doesn't have to decay. Okay? It's a statistical law which holds only for very large number. So I normally try to test students on the range of validity of the equation. Okay? So there are 3 or 4 good practices that I've told you about. Okay? In addition to that, for example, I didn't explain what is meant by scaling, for example. Okay. Here, you might say, what kind of scaling arguments are you talking about? Okay, where is it going? Scaling arguments. Okay. A good example to give of scaling would be the bypass surgery. Your artery is clogged. You make another bypass, which is, say, twice the diameter of the clogged artery. Okay. The gain that you get, the resistance fall, the student has to realize scale that's 1 over the diameter to the power 4. So you get a great advantage. Even if you unclog and even if you do a small bypass, which is just twice the size of the clogged artery. Okay. So one should know if the scaling law is 1 over a to the power 4, where a is the diameter or something. So one doesn't necessarily have to do all questions which are numerical. I would say that you should inspire visual thinking, avoid excessive reliance on memory, and socio-culturally, you must be gender sensitive. Okay. The old exams were very male-centered, and we should not be. And one should not use terms as they were used in the previous PISA test, which are not understandable to a student in India, to a high school student in India. And you have to avoid the drudgery and a mix of problems. Show some environmental sensitivity in your questions. Okay, so that is good practices. So I've told you what is essential, what is perhaps a good practice from my experience. Okay, and I think you may add more to it. And then you have a checklist. I think I have another 5 minutes, and I will be finished with that. So the thing is, you're not infallible. That is the first thing that you have to learn. That is what I learned, at least. So there is a checklist. First of all, have you covered the syllabus? Okay. Are your questions in different areas, or they are sort of crammed into one single area, like having all the fielders on the leg side or something? Okay. You sort of cover the whole field. Okay. You also compare it with the previous 3 or 5 years question papers to see that there is no inadvertent repetition. And very important, and every exam you show me, I'll show you these mistakes. Is there a spelling mistake? Is there a grammatical mistake? Is there a text versus figure mismatch, which always Invariably, this is the biggest error that happens, and a question needs to be dropped. You say, see the above PV diagram. And instead of PV, it is TV because you have changed it along the way. It's temperature versus volume. Okay. So check for figure versus text mismatch. And please avoid ridiculous physical situations and answers. Let me give you an example of ridiculous situations and answers. Just one or two, and I think I would be done. This is the JE problem in 2002, problem 8. Okay. It's about a parallel plate capacitor. There are two metallic plates, A and B, each of area 5 into 10 to the minus 4 meters square, and they are placed 1 centimeter apart. You are asked to find out, say, for example, the electric field in the middle. Question is not relevant. What is relevant is that you are asking them to use an infinite parallel plate capacitor formula. So the distance is 1 centimeter. Naturally, each of these sides must be at least 10 centimeters or more for your approximation, which I've written down here, Q minus Q, to be valid. But it is not, because this side is 0.23 centimeters. You take the square root of this, 5 into 10 to the minus 4. You get about 0.25 centimeters. So x by L is 1 by 4. It is certainly not 1 by 10 or 1 by 100 as you want it. If I were a good student, I would say this question has no answer. I cannot answer it right now. Give me 3 hours and maybe I'll work it all out. Okay. There's the JE question paper. Another JE question paper. I'm deliberately picking questions from the joint entrance exam, advanced. In those days, there was no mains, to show how even the best can make mistakes. A truck has an acceleration, it says, of 9 meters per second square. You go and check the paper. I'm not making this up. What is the acceleration after 5 seconds? Okay. You can work it out. The problem, it is not difficult. It is 45 meters per second. It's 162 kilometers per hour. Okay. Highly improbable. Which truck ever goes from 0 speed to 162 kilometers per hour in 5 seconds? It doesn't happen. Ridiculous. Another checklist you have to make is totaling. Make sure your total adds up to 10, or your 100 or whatever it is. And make sure that all information is provided. They are not supposed to remember G. They may, you can tell them you take it to be 10 or whatever. So these are the kinds of checklists that I'm saying. Okay. Cover the syllabus, compare with previous years, check for spelling mistakes, figure mismatch, ridiculous situation, totaling errors, information provided. Have it checked by a moderated, I'm saying, by somebody. Do not think that you are infallible. Okay. And even the best people can make mistakes. Another example, I'm thrashing joint JE papers now. The 1992 JE problem. There is a very famous problem. I know many coaching classes do this problem wrongly, of course. An insect is falling. An insect is falling on a rod, okay? And the rod is rotating. As soon as the insect falls, it starts moving towards the end. And the question is, how much time does it take to go to the end, assuming that it is, oh, my time is up, so I'm done. I'm sorry, I'm done. Oh, why is it going down now? How much time does it take so that it reaches the end? Okay. And look what the problem says, it's moving with constant angular velocity. Okay. If there's a rod hinged like this, and there's an insect here with some mass, it cannot move with constant angular velocity. So these are the kinds of mistakes. We are all not infallible. Best to get it moderated well and to be humble. Okay. So then you do, after that, there's a denouement. I'm sorry, I don't have time to do the entire denouement. What is the average score, the standard deviation, the median, etc. But I will tell you one thing. Before you set the question paper, it's a 4-choice question paper. The minimum, A, B, C, D, if I don't know anything, I'll pick anything I want. So out of 100 questions, I'll get 25 of them right by doing nothing, by being a monkey, by just marking whatever I want at random. What is the maximum I can get? 100. So 25 versus 100 is my range. What is half of that? 75, that is 37.5. To 25, you add 37.5. that is 62.5. That should be your average. Before even you give the test, that is the kind of average you must aim for. Halfway between the theoretical minimum and the theoretical maximum. Okay. There are 4 questions. I will mark any one of them. If I'm a monkey, I'll get 25 of them right. Okay. So 62.5 is the, and 1/6 of that should be a standard deviation. That is the rule of thumb. Okay. That's it. What is wrong with all these multiple choice questions that we see floating all around? It's a 4th choice. You are given only 4 choices. So it's a one is right. You're not given 100 choices. The situation is not fully described. So you have to tell them to make the correct choice. And there's digital marking. Okay. The other thing which is wrong is what comes from the Mahabharata. Okay. It is like the Yaksha episode of Yudhishthir, where the Yaksha asks all kinds of random questions. Who is greater than the father, than the earth, the father? Who is the most forbearing than the earth, the mother? Okay. What is the greatest? I mean, they're all random, coming from all sides. What is the greatest? What is the greatest? How should I put? Most strange thing in this world? Oh, every day I mean, of course, he knows the answer, so it sounds very good. Every day you see people dying, but you don't think you'll be one of them one of these days. Okay. So I don't like it because all questions come fast and furious, unrelenting and random, unconnected, demanding an immediate answer from Dharmaputra. Okay. So उतना अच्छा नहीं लगता है ये सब करके. जैसे कि ओलंपियाड वाला क्वेश्चन करते हैं, I have 3 hours, 5 hours and only 3 questions. Even if I do one, I feel happy. Okay. Right? So regarding the analysis and other things, this paper, Physics News, is something that I would request you to look at. It is also there as the first paper in my ResearchGate. So you can go and download it from there. You can ask Poonam ji and Ved Srivastava ji to give it to you. The second paper is also good in the American Journal of Physics. Thank you. Thank you very much.
Okay, thank you so much, sir, for such a wonderful lecture. There are many questions, sir, in the chat box, so I read one by one. First question is from Mr. Prasad Yadav. In the present scenario, it is becoming very difficult to teach physics, especially derivation of expression and solving problem. What may be the possible way to take such a problems?
Very difficult question. Okay. It is advised that you do not go through an elaborate derivation. You are advised not to go through an elaborate derivation in your presentation. Okay. So basically what I do is all, and this is not the best thing. I'm not saying मैं सबसे बढ़िया कर रहा हूँ. If I have a long, like yesterday I had to teach students Hartree-Fock method. It requires a lot of manipulation. So I just orient them a little bit with 2 pages of writing, and I give them a derivation to read up. Next lecture, I ask them if there are questions. And there are many questions. So it is never advised that you do a very elaborate derivation. There are 2 or 3 things you can do. You write a short note on this about what you want to do. I have a blackboard, not here, but when I'm at home, I've bought a blackboard, a whiteboard. I do part of it over there. Usually in the second session, not the first session, and I make them, I do it for them on the blackboard. Right.
Thank you, sir. Next question is from Dr. Partha Goswami. He asked 2 questions. First, what are the guidelines for MCQ answer type questions? And second, please emphasize the importance of good distractors in framing MCQs.
Yes, I have not spoken about it. It is described very well in my, how should I put it, in my article in Physics News, the importance of distractors. Okay. The distractor is the wrong choice. Okay. The distractor is the wrong choice. Okay. There is one choice which is the best choice. Other 3 choices are not good. They are wrong. If I am doing an elimination test or an institutional test, I want students to choose the correct choice and avoid the distractor. If I'm doing a misconception study, If I'm doing physics education research, it is the distractor that I'm interested in. How many students pick the distractor? If the students pick the distractor, then I know that this is a good misconception that I need to clear up when I'm teaching the next time. Okay. The distractor is important, number one, because it tests whether the student knows, uski buddhi sukshma hai ki nahi. And number two, okay, it also informs the person who is setting the paper, this is something I'll have to clarify the next time I teach the subject. तो खराब चीज नहीं है, बहुत अच्छी चीज होती है distractor.
Okay. Thank you, sir. Next question is from Miss Anshu. The online mode of teaching these days, many software available to conduct online tests like Google Form, Microsoft Team, etc. Which software, according to you, is most appropriate in conducting online tests?
I have really not checked them all, to be honest with you. I have done Google Form. See, one thing is that with any online test that you conduct, the possibility of malpractice by the student is always there. Okay, whatever you do. Okay. So there is no form, there is no one which is better than, I cannot answer the question because I've only done Google Form. So yeah. I'm not the appropriate person. Yes. And I don't think anything that you do, except if you make different tests for different students. Slightly different tests.
Yeah. Next question is from Miss Neeta. CBSE has introduced case study based on questions in the sample paper. Please throw some light on it.
Say that again, repeat the question.
CBSE has introduced case study based questions in the sample paper. Please throw some light on it.
I haven't gone through it in detail. Okay. It is a good idea to have case studies, but I mean, these are all, I would say, you ask the question, you make the question socially relevant. That is it. Case studies means, okay, you put a case study in there. It would make it socially relevant. That is fine. I mean, it's a good idea, but okay, that's all.
Okay. So, sir, due to paucity of time, I cannot take more questions.
Right.
So let us thank our speaker.
Right, thank you. Please send me some of those questions, or I will look at the chat.
Sure, sir.
Yeah. Thank you very much for your time, Yogesh ji, Poonam ji, Ved Srivastav ji, and all the participants.
Yeah, sure, sir. So over to Poonam ma'am.
Thank you, sir. Thank you so much, sir, for the enlightening lecture, especially the example you quoted for the time reversal symmetry. Thank you so much, sir. Now, we are honored to have the opportunity to hear again from Professor V.B. Bhatia. He is former professor of physics, University of Delhi, and he is going to speak about practical work and its assessment. Welcome you, sir. Sir, you are on mute. Kindly unmute yourself, Bhatia, sir.
Am I visible now? We are audible now?
Yes, sir. Yes, sir. Sir, I think there is some network glitch because sir's video is paused. Yes, absolutely fine now. Thank you, sir.
I'm going to talk about practical work and its assessment. This is one of my pet subjects these days, or according to some friends, it's a pet peeve these days. But before that, I must congratulate my previous speaker, Professor Vijay Singh. I think he made very, very relevant and valid points, especially those where he said that the question should contain only those things which are relevant. I mean, you can't say I have infinite speed or this kind of thing, you see. those are not relevant. So I think he made very important points, and I think he was it was a very good guide to learn to make questions. Thank you, Professor Singh. Now coming to my talk. You see, the talks yesterday by Professor K.P. Ramesh and today by Professor S.P. Singh, who were talking about the undergraduate courses in their institutes. And I learned that they listed a lot of practical work, a lot of experiments to be done by the students who take admission to these undergraduate courses. That means they attach so much importance to practical work in physics. And I therefore am highly disappointed that the practical work in our school labs is in such a pathetic state. And I imagine the kind of thing that, therefore I chose this occasion to vent my feelings, so to say. And I specifically asked Professor V.P. Srivastava if I could talk about this. And he was very kind to allow me to do this. Now, what if lab work is not done? What is it that the students don't get in schools? These are some of the skills that a student can acquire if there is meaningful practical work in our lab schools. Accurate measurement of various quantities, planning an experiment. I'll explain what I mean by this. Presentation of data, problem with that also. Ability to use tools of calculation. This is, of course, simple log tables and tables of trigonometric functions, elements of differentiation, calculation, etc. Sharpening of self-expression by discussing results. This I'll come to later, and along with the boosting self-confidence by formulating and answering relevant questions. And the last point, making good graphs and interpreting them. You see, my own experience, even at higher level in honors classes and in MSc classes, is that students cannot make very good graphs. Most of them. I mean, there are some who are very good, but we must start training them, making graphs and interpreting them as early as possible. You see, these days our magazines, our TV screens, our newspapers, they're full of graphs, and we need to interpret them. Therefore, I think this making good graphs and interpreting them is a very important tool or very important skill that a student must acquire. And part of it can be acquired in a lab. Okay, I'll skip a few slides because this is measurement. All the measurement ultimately boils down to knowing the least count. You see, even in higher classes, I have seen students struggling with finding least counts. So I think 11th and 12th class are the right places and right time to learn about least counts, so that later on in life, the students do not have any problem. So I'll skip these slides. Measurement of time, that just a moment, because now most of the watches in our labs are digital watches, and conversion from a decimal scale to sexagesimal scale can pose some problems, but they can be solved. Planning an experiment. I think this subject is very dear to me, because I've seen students going about their work in a very irregular fashion without any planning. So I'll illustrate this with a simple example. You see, suppose you ask a student to give say, a piece of wire or a conductor, a small length of a tube or something, and ask them to verify Ohm's law. So what the student does is to have a certain potential difference across this, measure the current, and then plot the current against the potential difference, and then the slope. If he wants, he can find the resistance. This experiment is very simple, but the question is about the apparatus that the student has to choose to do this experiment meaningfully. Suppose you are given a battery of 2 volts, and that means and you apply that 2 volts in a preliminary sort of experiment to that conductor and see how much is the current. Suppose the current is of an ampere. And if you are given an ammeter which reads from 0 to 10 amperes or even 15 amps, I'm sorry, that's not going to do the job well. What the student needs is an ammeter from 0 to 1 or 0 to 1.5 amps, at the most 3 amps, because otherwise the reading would be too coarse. Similarly, about the voltmeter, the student has to have a voltmeter which has a range of at the most 0 to 2 or 0 to 3 volts. Again, if the poor fellow is given a voltmeter which has a range from 0 to 10 or 0 to 15, which many labs have, they don't have voltmeters with smaller ranges. So if you give that, obviously the experiment is going to be very coarse. And if he's honest, if the student is honest, then he may not or she may not get the kind of result that he or she is looking for. Similarly, suppose you are asked to do an experiment to find the focal length. Given the optical bench in your school, you know how much space you have for the object to be moved and how much space you have for the image to be formed. And I think you can choose a mirror or a lens in this case of appropriate focal length, so that your observations are like this. You see, they're all well placed, and the image is formed. Certain freedom to choose the apparatus from the lab. But I think this is a good idea to allow students to choose their own apparatus. For this, of course, you need well-equipped labs and you need more funding. And I hope NEP 2020 helps the schools in setting up good labs so that students can do meaningful work. Are given the option to choose, then the student can plan an experiment so that the observations are well scattered. So that later on, if a graph has to be drawn, then he can do he can draw a good graph. Similarly, presentation of data. I'll just hurriedly go through these because I don't have much time. You can see here 19.2, 33.5 centimeters, 23 is jumbling, you see. You start with 19.2, jump to 33.5, jump back to 23.7 and like that. You know, if the student knows that if U is varied in a certain fashion, V varies in a certain fashion. That trend you can find out if you vary U regularly. Now here, the U is being varied regularly, but again, I don't like somewhere the difference is 4, somewhere the difference is less than 4, somewhere it is 2, and so on. I mean, a good experimentalist would choose observations such they're equally placed if there is space for this kind of thing. Similarly here the observations are better, but again, you see the differences, they're not equally placed. And to my mind, this is the best thing to do, what we can do, if possible. 20, 25, 30, 35, 40, 45. And of course, you'll find where the image is formed. So I'll skip this. And once you have done that, then you must know how to calculate. So you must not confuse the two formulae, one for the mirror, one for the lens. You must know your convention, sign conventions. So you assign proper signs to V and U and so on, so forth. And if you are chosen the correct formula and found the focal length, I think a good experiment would like to know whether the result is correct or not. So probably you can back calculate and find out whether the result is correct or not. And some students do it, but most of us just ignore. Once the focal length is found, here it is. We just don't bother about it, whether it's correct or not. Yeah, I'm sorry this is hidden here, but this graph was taken from an NCERT source, and you can see, you can also verify the focal length with the help of a graph. Boosting self-confidence. You see, I think this is a very important thing. If lab work is structured as an exploration, as I'll later on suggest, then the outcome of every project or every experiment must be shared with the class. And you must explain, you must defend the results that you get. You must explain why you got these results, why the results are as they are. So if you want to defend that, you'll have to get questions from your colleagues, from peers, and prepare answers for those questions. This kind of interaction, defending and getting questions and answering, this kind of thing can boost your self-expression, can boost your knowledge also sometimes, and can sharpen the self-expression of students and boost their self-confidence by formulating and asking relevant questions. I've talked about drawing graphs, and I can only inform you that in NCERT class 7 book, we start teaching how to make graphs and expect students to learn them and be efficient graph makers when they go to higher classes. So as I was going to prepare this talk, I discovered accidentally, see, I didn't know that this manual for practical work existed in NCERT. I found this on the net and I went through it. And I think it's a very well written manual, detailed description of experiments and suggestions for activities, projects, and so on. Very well written manual. And it can be guide for every teacher if the teacher wants to do really good work in the practical class. So I wonder then why practical work is not done in our schools. And this is what I have been able to gather. These are some of the factors, maybe there are more, and I have not been able to list them. First, ignorance and apathy of a large fraction of teachers. I'm sorry, I cannot put it more politically. Ignorance and apathy of school management at all levels. This I can understand. Non-availability of adequate lab space. This again I can understand. Non-availability of good quality equipment and instruments. This I can understand. But I cannot understand ignorance and apathy of large fraction of teachers. And this is a racket now these days. All schools tend to get marks for their students say between 28 and 30 out of 30. This is a racket, and this is well known. It is talked of, but in private. It's not talked of in public, but it's a racket. The schools vie with each other to get more marks for their students in practical. And I think I'll suggest what can be done. So due to these factors, the practical work has lost all meaning. So as far as the first factor, ignorance and apathy of teachers is concerned, I think our teacher training institutes may be largely to blame. I'm sorry to say that. Because they should train teachers to do practical work in the training institute and then handle it when they go to schools. It's quite possible that the faculty, at least a part of the faculty of these institutes, do not by themselves, being the product of this system, may not be interested in this, may not be able to handle vernier calipers and traveling microscopes and whatever the apparatus is needed. So these faculty members either fail to appreciate the importance of practical work or do not feel confident enough to handle various pieces of equipment. Obviously, the product of such teacher training institutes will be unable to do the practical work of the students. It's a call, at least from my side, it's a call for teacher training institutes to pull themselves up, because it is they who are responsible for the training of teachers. And if their trained teachers are not able to get or do practical work in the labs, I'm sorry, it is they who have to blame. Ignorance and apathy of school management, I can understand, although this is not the correct thing. This stems from ignorance of nature of science and experimental area of knowledge. A lab in a school needs space, a lab assistant maybe, and regular funding. The management finds it's very cost prohibitive. I remember once I was going with a university official to some college, and he asked me, "Sir, can we not teach science without labs? Because labs are very expensive." So similarly, these school managements, they are also asking the same thing. But if there is enough funding from, I hope from NEP 2020, maybe the management can change its stand. Ignorance, the management of school measures the, see, this is again an important thing. The management of a school measures the success of the school from the number of their students selected for IITs and medical institutes. In the competitive examinations for these institutes, competence in lab work is not required. So the management and the parents think, and rightly so, that the practical work is a waste of time. So in that case, the management would be right. So we must find some way of making practical work important, even for selection in IITs and medical colleges. I'll have a suggestion, but later. Non-availability of good equipment, of course, this can be circumvented and we can go that. Again, let me, what is this that the students are actually, if we don't do practical work in our schools, what are we doing? We are harming the students because they don't learn the necessary skills. We are harming the cause of science. You see, science is an experimental based area of knowledge, and no theory is acceptable, no idea is acceptable unless it is backed by experiment, not only once, but several times. So therefore we are harming the cause of science itself, and to some extent, the cause of development of our country. This point was made by Dr. D.K. Aswal in his lecture in the memory of Professor Vedratan. And I knew Professor Vedratan. He himself was votary of a good practical work in the labs and its inclusion in competitive examinations. Let me skip these because I don't have time. Yeah. A test for the practical skills of all students who appear in competitive examinations does seem impossible. There are lakhs of students, and how do you test them? But I have a suggestion. If possession of minimal lab skills is made a part of counseling process, you see, out of those lakhs, each institute calls about a few hundred students for counseling. And at that time, they can test the students for their competence in lab work. If they can do that, it's not difficult because there will be a few hundred students and the counseling can spread over several days. So if they can do that, they'll be doing good service to physics and good service to lab work in our schools. So probably they can do it. I'm not sure, but I think they can do it. Let them think about this. There is this now this talk which has been suggested by NEP 2020 from class 9, 10, 11, and 12. I don't know what way or in what form it's going to be accepted later on. But to me, it's very disturbing because earlier we had students going up to class 10, receiving general education, including mathematics and sciences. And therefore, one expected that once they resumed their duties as citizens of this country, they would at least have some knowledge, some basic knowledge of maths and sciences, and they would be able to decide things in a better way than without that knowledge. They would also be maybe inclined towards what we know as the scientific temper. But scrapping this, I think, is very harmful to me. Yes, suggestions for revamping the lab work. These are general suggestions and probably they have been made many times. So I would like to make laboratories places of exploration rather than of doing experiments with fixed outcomes. I have experience of students, even the universities struggle with these counts. I've already talked of this. So it is better if the students are made familiar with all the operators that is available in a given lab and they're allowed
Sir.
to calculate.
Yeah, I'm sorry to interrupt you, sir. We have another 5 minutes to wrap up the session.
Well, I'll try. Thank you.
Yeah, okay. Thank you so much, sir.
So allot time to students for the experiments that they would like to do. Some students want to do something which may not belong to the course that he or she is doing in the school, but something, say, some electronic project in which he or she is interested. I think our labs should provide facility for that kind of thing so that the students are drawn towards the lab. So let me skip these. Yeah, there's just one small suggestion that instead of letting the students prepare the practical notebook, which is very time consuming, we can provide them with write-ups and we can provide them everything ready-made, the tables in which the student just inserts the observation and graph sheets on which the student makes the graph. Everything is there. And once he has done the practical, once he has gone through the evaluation of that practical in the class, he can store it in one of the files as a record of his practical work. Assessment of practical work, that's very important because this is a very thorny issue. Yesterday, Dr. Punita Verma, I think, was talking about assessment of practical work but in undergraduate classes. I'm going to talk about the school level. I think what we have to do is to assess the student on various skills which go into making a good experiment. So what are those skills? All aspects of theory associated with the experiment, of course, handling of apparatus, various measurements involved, planning an experiment, tabulation. I've already gone through all this. And these are the skills that we think a student should acquire. And therefore, we should test all these skills, not just one outcome of the experiment, but all the skills. I'll explain this. I'll just take a few minutes. I'll explain this with the help of an example. Suppose the student is given to determine the focal length of a given spherical mirror. Right? Take a very simple example. Then if I were a teacher or I were an assessor, I were an examiner, I would like to know how the student handles the mirror, whether he handles it like this or like this from the middle. Finds out what kind of mirror it is. I mean, by simple examination of the surface, the student can find out. If concave, if the student finds that it's a concave mirror, does the student find the approximate length, focal length by focusing rays from a distant object so that he knows approximately what kind of result the student is going to get later on. How does he place the lens on the optical bench? Does he leave enough space for U and variation of U and the finding out the image space? That is management of the optical bench. How systematically does the student vary U and V? I've already given you examples. I would like to see him to be systematic. How the student records observations with units. I mean, I know several times students forget to put units along with the observations, and I would like to see whether the student has done that. How does the student draw a ray diagram? What sign of calculated focal length does the student expect? That is the student aware of the sign convention? Does he get the results close to the approximate value? He found or she found the approximate value. So does the result tally with that? If not, why not? Does the student seek an answer? Does she or he verify results by drawing a graph and making back calculations? These are some of the general observations. An experienced and vigilant examiner can add a few more points. And my last suggestion, and probably not something that is going to be liked by many people, is abolish annual practical examinations. Let the teacher in charge who has seen the students working throughout the year grade the students based on a range of skills and listed above and submit the list to CBSE. The rank or grade will be shown separately from the score in theory. This would avoid the tendency of the schools to award marks to their own students. And then it is for the institutes admitting this student or employing this student to decide if they want a student who excels in practical work. I'm aware that some of these points are made may be controversial, but if lab work has to be made effective, some drastic measures may have to be taken. One thing is clear: to push the agenda outlined It's imperative that schools have well-equipped labs where quality equipment and instruments are available. I hope that NEP 2020 will release generous funding and the schools will revamp their labs and rejuvenate lab work. I have a sample write-up of projects for studying the various aspects of a simple pendulum. This is pretty long, so I won't go into that. I would suggest that if you want, you can, this is, the script is already with Professor V.P. Srivastava. You can ask him to share with you, or you can visit my website, which is there on the first slide itself, and see this. Thank you very much.
Thank you, sir, for very informative on practical work and its assessment. Sir, you put it very amply. Thanks for guiding the participant as there is no question in the chat box. So let us thank our speaker. Thank you, sir. Now I hand over the session to Poonam ma'am.
Thank you so much, sir. You have again given us the honor to listen you on the topic practical work and its assessment. I am highly obliged. Now I request Dr. Atul Modi, former Associate Professor of Physics, VES College of Arts, Science and Commerce, Mumbai. He is going to speak on the topic Designing Instruments of Physics Learning. I welcome you, sir.
Yeah, thank you, madam. Am I audible? Could you hear me? Hello?
Yes, sir. I can see you. And you are perfectly audible, sir. Hello. I think there is some network glitch because Atul sir's video is paused. Yes, sir. Now you are visible. Kindly speak out something so that we can check the audio as well.
Yeah, I'm trying to change my
Um,
yeah.
Participant. Yeah.
Can you hear me now?
Yes, sir. You are absolutely
Yeah,
audible.
I have switched my internet network, so that should
Okay.
solve the
Okay, sir.
problem.
No problem.
Yeah. So you want me to start now?
Yes, sir. Please. If you
Uh,
want to share your slides, you please carry on with that.
yeah. Uh, it's 11:51. So I suppose I have half an hour.
Yes, sir.
Yes. Yeah, I'm putting it on screen share and
Yes, sir.
okay.
It's absolutely
Yeah.
fine.
Can you see my screen? Yeah. Fine. Just a minute. Yeah. First, before I uh, define what is instrument of physics learning, I'll just tell you the plan. What I'm going to talk about is what is known as problem-based learning, uh, uh, teaching, learning, and assessment. I mean, assessment part I will not talk much about because it would require much more time. But we'll talk about teaching, learning using problems. Normally, problems people see. You have heard Professor Vijay Singh. You heard Professor Rajaram Nityanand yesterday. We always use problems as an instrument of assessment. We use them for assessing students. We never consider that it's a part of learning process, and our learning always focuses only on theoretical aspects. So that's what I'm going to talk about. I'll spend few minutes for discussing some educational pedagogy. And then, of course, I would uh, show you some of the examples of what I'm thinking about problems. So I have some problems listed here. I'll talk about real isotherms, phase diagrams, superposition of waves, modeling of Earth's atmosphere as a problem, inelastic collision problem, physics of sun, relativity with space-time diagram, and general relativity. All these is the bare minimum I can show you in the stipulated time, so that I can illustrate how learning can happen when students solve problem. This all started actually when I started teaching. I realized that if I give a very easy problem so that students don't miss out in the exam, something as simple as, in a crude way, I will say that if I just describe in a sentence that if x is equal to 2 and y is equal to 3, then calculate z is equal to x plus y. They would simply not do it, just because the moment they see it's a problem, their mind is switched off. And so my issue was that I see students as very intelligent ones. In every behavior of theirs, their intelligence reflects. But when it comes to physics, they behave very dumb. And but if you ask them straightforward theory or derive this, derive that, discuss this, describe that, they are all very good with it. And so it was a bit of challenge how to get them involved when I'm teaching physics, and how to make them do well in their career once they graduate, not necessarily physics. So I will give this, I would dedicate this lecture to one of my teacher, Professor S.H. Patil from IIT Bombay. So when I joined there, you see, I went from a very uh, normal college system, and we were never used to doing any problem. And then the kind of physics we started doing at a higher level became much difficult to handle. But this teacher of ours, he would take 1 hour of tutorial every week, which would invariably stretch to 2 to 3 hours, and he would actually make us do problems. And that became a great formative years of my learning physics. And later on, of course, once he told me, you see, he said, physics teaches you to see things in the right perspective. So you see things, learn to see things very clearly in its totality if you have this capability. So that's what I tried doing as a teacher with my students. So the problem-based learning, once I did all these things, I realized that there are people who are across the globe working on this kind of ideology. See, your traditional methods are teacher directed. So teacher comes and delivers lecture. Then he has this syllabus which he delivers to students, and students are supposed to just learn, memorize whatever it is. And students are just the recipient of knowledge. They are not people who are actively involved. Now, if you switch to this activity or problem-based learning, then it's a problem motivated. Then students actually as a problem solver, and the role of teacher is like a coach. It's a coach mediator. So coach only provides a framework, and students actually proceed with the learning part. So students have variety of styles of learning, their own pace of learning, and coach role is to just guide students to see that they keep on progressing. And that turned out to be not just a joy to students, to me also as a teacher. And when I see now actually Vijay Singh has talked about this designing problem. So this is just a sort of an exercise. I'll quickly rush through. When you students do problems, they start appreciating theory. They just start justifying theory. Problems can justify. You can teach students using problems how to exploit symmetry, be it physical, geometrical, or abstract mathematical. Even logically, you can have a symmetric situations. There could be interdisciplinary problem. So students can learn different area, subject other than physics, also using physics problems. The Today morning, the session, Shiv Nadar University, they talked about a student going into economics with his physics background. And then we can also teach much higher level facts, even with a simple physics. I would be able to illustrate this to you with a problem today. Of course, order of magnitude gives students all the ideas about what kind of numbers we are dealing with, what kind of size, strength, etc. There could be open-ended problem, which means the solution is not known. But then you have to really analyze it critically and creatively. This is, of course, more so for the research people. But even at a lower level, we can always pose such kind of questions and problems to students. Problems definitely would illustrate applications. It would definitely help student strengthen their mental ability. Uh, am I audible? I hope I have not lost the audience.
Yes, yes, sir.
Yeah,
You are audible.
yeah. So one a student can correlate this principal observations and physical quantities. Their grasp of experimental techniques automatically gets enhanced. Professor Bhatia was just talking about giving importance to experiments. You see, 90% of the experiments occurs in person's head and 10% outside. But 10% efforts in your head and 90% of physical efforts outside in carrying out the experiment. So unless your 90% of planning in your head and the analysis occurs, the experiments don't get you result. And unfortunately, when we are carrying out the labs, this 90% of work which is done with head is not given importance. That's where we lack actually. So one of the job is to challenge. The learner should constantly be challenged with task that refers to skills and knowledge just beyond their current level of mastery. This will capture their motivation and build on previous success in order to enhance the confidence of the learner. I mean, this word enhance the confidence of the learner. I've met students with who have scored 75%, 80% in graduation exam, but are not confident enough to accept the challenge. But I have simultaneously I have met students who are very confident, irrespective of their examination performance. So problems definitely can play. Our experiment with this method of teaching has shown that actually it works. I mean, this is words of Richard Feynman, whom everybody would respect. And he says that I think one way we could help students more would be putting more hard work into developing a set of problems, which would elucidate some of the ideas in the lectures. Problem give a good opportunity to fill out the material of the lectures and make more realistic, more complete, and more settled in the mind of the ideas that have been exposed. So actually, personally, I feel that 90% of learning takes place when students actually do this problem. Only 10% happens in the classroom when a teacher delivers on the board. This is, of course, a very famous person's pedagogy. It's called zone of proximal development. When student comes to class, they come with certain capabilities. And then the zone of proximal development is the distance between the actual development level as determined by individual problem solving and the level of potential development as determined through problem solving under adult guidance or in collaboration with more capable peers. Now, this is, of course, they call it scaffolding. But the point is, when a teacher exposes student to a problem and supports his actually solving the problem and the learning process, then student advances in his capability in his zone of proximal development. Uh, uh, the last part of the philosophy, the cognitive aspects as described by Schoenfeld is the resources. Resources are the physical knowledge that a student possess or what we deliver in the class as a teacher. That's called resource. Then there is a heuristic. It's the technique which students learn, like the solving problem, exploiting symmetry, etc. Now, these can be delivered only by exposing them to problem solving. They learn control, that what physics is applicable where, what is the idea and what is its how effectively it can be used in a given situation. So that's all control. And then belief system. When I described the earlier experience that the students were not confident to address even a simple problem, their belief was bad. Their belief system was faulty. They thought they were not capable of doing it. And our experience have told us that actually this exposure changed students' belief system completely. I won't be able to go much into the detail. But what has happened is by solving problems, their resources were enhanced. Heuristics they learned, control is there was an improvement, but the belief system was a drastic improvement. In fact, it is at this level, the belief system is where everything makes a difference, because what happens in that case is students start taking initiative on their own, and they don't look for teachers help, because they start believing in their own ability to be able to do things of their own. Now, what kind of problems? Vijay Singh has talked about it, so you already know. You want the basic principles to be incorporated. That should be rich in context. He has already told you about it. Should be difficult, not too difficult that they would be simply turned off. Not have a repetitive patterns. Should have a reasonable goal. That they should feel that I have achieved something when I solve this problem, and it should guide students to comprehend what they have supposed to learn. Now I'm coming to an examples. Now this is definitely not a mathematical problem. It's more a qualitative one. But students can be challenged. Now this is of course isotherms which are already shown in 11th standard textbooks of NCERT. So what we can ask is, using these isotherms, explain how the LPG cylinder works, or even cigarette lighters these days, which are transparent and you can see the liquid inside. And students would have to struggle to correlate the functioning of this liquid petroleum gas, because what you see here is a gaseous form, you see here is a liquid form, sorry, so gas to liquid transition and the liquid part of the diagram. And I'm not going to discuss the solutions, but I'm just showing you example that this becomes a very interesting exercise. Students start seeing meaning. Thermodynamics otherwise becomes too abstract unless you can correlate with the day-to-day life applications. This is another one. It's a phase diagram of pressure versus temperature, or water especially. You can explain using this phase diagram how pressure cooker works, how you can your snowball works, or we eat this barf ka gola in summer, and how that works on phase diagram. And then you can see the actual phase diagram, which appears to be very abstract, would have a physical meaning, and students will start visualizing phase diagram with the real life situation. Uh, this is an example which I would suggest, and I have made students do it, and they really enjoyed it. I mean, otherwise it's an abstract mathematical theory, but you plot two SHMs which are having same frequency but are shifted by some small phase difference. So the red and blue are those two SHMs, and if you add them up mathematically, of course, the green one results, which is also an SHM with the same time period. But more interesting is, once they have learned how to do this with Excel. Now these days every student has a mobile. All mobiles have Excel, the Android app ones, and can be done in class very quickly. Teachers will have to, of course, try themselves first, and then tell students how to do it. And when students do themselves, it becomes more sense to them, instead of my just flashing a diagram in front of them. So you have here two SHMs which differ in phase, sorry, by small amount in frequency, and if you add them, that's what results. So this is actually done. You see, before Excel, you would not want student to take calculator and calculate such complex wave pattern. It's very time consuming affair. But Excel or spreadsheets have given you tremendous power to see this kind of graphs immediately, instantaneously on screen. So what is there in textbook, which appears to be very abstract, how they arrived at this pattern, what happens. Of course, you can always demonstrate. There are enough videos available to demonstrate these wave patterns, but this could be a very interesting exercise. Similarly, actually, what I did was, this work was actually done for NCERT when we were developing some teachers training material. You can see series 1 and 2 are the incident and reflected wave, and the series 3 is the addition of the two. So you have an incident wave and reflected wave, and they are added at different time of one time period. So I have got some 7 or 8 such frames. And if I put all of them together, the addition looks something like this, which means if my time period is less than 1/10 of a second or frequency is more than 10 hertz, then you will see more than, uh, our eye resolution is only 1/10 of a second. So in 1 second, you can see 10 such string positions. And if the frequency is increasing, you are seeing more such positions. So actually, it looks like a loop, what we physically see. But actually, it's a combination of so many positions of the string. Now that's very clear. I mean, so it's a problem. It's very simple. It's an exercise. People just do it, but it's a joyful work, and then the understanding it adds to your the learning of this process. Now, this is a very interesting problem, the modeling of Earth's atmosphere, and it happened very accidentally. So if you actually do, most of the textbooks show you how to calculate variation of pressure with height. And then you will arrive at this exponential formula here, where Z0 is what you call as a scale height, uh, and so on. Now, what happened was actually one fine day, okay. So if you look at this, you can estimate the scale height. Mount Everest peak is about 8 kilometers high. Now, actually, it so happened I was just flying Air India flight 2014. And those days they used to show movies. That particular day, instead of showing movies, they were displaying temperature with height of the aeroplane. And what I did was I started recording height versus temperature just before we landed. You can say this is about half an hour's time slot. And so you assume that in that half an hour, whatever distance the aeroplane traveled, there was no change in temperature with height. At particular height, temperature had remained same during that horizontal distance. So that's a small assumption we have to make. But what I decided to do is, let me see, because the earlier pressure versus height formula that was derived was an isothermal model. That means we are not considering variation of temperature with height. But now that height temperature varies with height, and if you actually want to do the modeling, I've just plotted this with simple Excel, and you can see it looks almost a straight line. That's my straight line fit here. Uh, so the temperature has a linear variation with height. Actually, air is a bad conductor of heat, and an envelope of air rising does not exchange heat with surrounding, but cools due to adiabatic expansion as a result of drop in the pressure. So you can look at the problem. The temperature is dropping, and that's the equation. But what is interesting is when we do the analysis and the modeling, the temperature versus Z is this, and pressure versus Z is this. And uh, typically, we all believe that it's an exponential behavior, but it turns out to be a different kind of behavior. You take air as a diatomic molecule. Of course, if you take gamma almost going to 1, that would be more an isothermal model, and then you would get your linear behavior. But otherwise, uh, gamma is 1.4 for diatomic gas, which is what air is mostly. So that's the equation of pressure versus height. So that's a very interesting problem. And this we can make students do in class. It doesn't have to be examination problem. But when they learn, when they do and they learn, that's what happens. I mean, let me give you an example. I mean, one of my daughter is going to art school. Uh, what they teach in art is hardly any theory, and then they have to do something in exam. It's basically in the morning, a teacher goes and poses a particular problem that this is the activity, this is the drawing, or this is what they have to create. And the whole day they are just busy creating it with teachers' assistance and guidance. I mean, of course, in case of physics, everybody is expected to get the same answer, whereas in art that doesn't happen. But everybody doesn't go through the same process of thought process. So when a student is posed this challenge and they go through this process of thinking, that's when the learning occurs. That's where the intelligence grows. So the problem is not what we teach them when they are undergraduate students. Problem is what capability they earn while they go through this whole process of learning. Okay, it's that capability which pays them great returns in their life. Unfortunately, we always hear this criticism that Indians are not good in creativity. But let me tell you, in art, music, we are the greatest people as far as creativity is concerned. It's only science where we are criticized. I'm not going to debate. We have done great work in science too. But this would definitely help enhance students' creative potential. Now, this is, of course, a JE problem that you have a neutron which collides with a singly ionized helium. And you want to find out what are the frequencies of the emitted radiation. And this neutron is scattered at 90 degrees. Now, of course, this is a class 12th level problem. Students have to use process of collision. They have to understand the structure of atom. But in this case, to challenge them, they have put a singly ionized helium. So they'll have to work out energy levels of singly ionized helium. They have to understand the elastic inelastic collision. Most students will not be able to solve this problem in the first attempt. But then we can always give them smaller problems uh, to support their thought process. And if they can't do this problem, okay, this is a smaller one. Why don't you try this? At least they will understand one aspect of the problem. Give them another problem. They will understand another aspect of the problem. So you are not actually telling them the answer. You are not showing them how it should be done. Teacher is not solving. Okay, it's not a show where students just appreciate what is being done on the board. Some people are asking about how do we communicate. This is a model of communication. We are not communicating by word. It's a non-verbal communication. We are posing a challenge, and they learn everything from you when they do it with your support, not by your telling them. That's one way. There could be many such possibilities. One can develop their own model. But this is the problem-based learning model. So the designing is one problem. I showed you one or two where I have designed those questions or problems. This is one a problem where uh, was asked in JE exam, and as Professor Vijay Singh said, it's likely that some problems may be wrong, but most of the time it's a committee which sets the problem. So some of these problems are really very good, very illustrative. It teaches students a lot of things about it. For example, they would learn here about what happens at an atomic level in an elastic process. They will think about energy levels of helium plus, so they'll go beyond hydrogen atom, etc., etc. So we have to pick such problems. We can, of course, improvise on these problems. We can support by some additional material to students, but it would be great for them. Now, this is, of course, having exposed them to theory. You are asking them to do some problems. So theory precedes when before they are exposed to this solving technique. But now here is a problem which also again based on the theory they learn. So to show this problem, I'll have to go back to, just give me a minute. I'll have to open my, yes. Yeah. Are you able to see my PDF document?
Yes, sir.
Yeah. So this is doing the model of the sun.
Sir, can you please make it full screen so that it will be in bigger in size?
I will just try. I'm not sure how it will happen, but let me
Sir,
see.
just go to the view button on the top panel in the
Yeah.
PDF. Yeah. And there is a full screen option. Yes, sir. Control L. Yes, sir.
Okay. I think you can see this.
Yes.
Yeah. So here is basically, we know, I'm going to say it. So it's not necessarily that you should read because we don't have that much time. But you have the solar luminosity with which we can use some basic physics, Stephen's law, Wein's law, and we can estimate surface temperature of the sun. And then we want to know how would the sun manages to radiate so much energy. And from the luminosity, we know how much energy it radiates. So how much it is managing to generate. So what could be the process of generation of energy? It could be gravitational energy, chemical energy, nuclear energy. And then we go ahead and estimate that if sun was to generate gravitational energy, the amount of energy it could have generated is this much, and then the time required is so much. And then this time scale is not sufficient. So that could not be the criteria of sun radiating, because we know sun is much older than what gravitational energy would shine for. Chemical energy is even worse. then of course nuclear energy fills our requirement. And therefore, we should know that if I want to generate this nuclear energy from hydrogen fusion, how much temperature is required. And this temperature has to come from sun's original gas cloud shrinking to the present situation. And so there are requirement, and the classical requirement again fulfill, but there are two possibilities. One is hydrostatic equilibrium and the other is quantum processes. And both of them actually fit the bill. And so this is one such problem which one can think of. 1
Excuse
minute.
me, sir.
Yeah.
Sir, can you
I know.
please wind up the session in 5 minutes?
Yes, 5 minutes. I know,
Yeah.
because this is the most important.
Yeah.
Here, what I'm going to show you is that how you can discuss theory. Okay, I think the full screen mode actually displays the entire page, and therefore it becomes much smaller. So if you allow me, I can show you my entire screen. Let it be other way. At least you can see some of these things and read it.
Yes, yes, please do. Please go back, go back.
Yeah, this is better, I suppose.
Yeah,
In
this
fact,
is better. This
I
is
can make
better.
it wider. I can make it wider.
Yeah.
Yeah. So now this is actually teaching relativity as a problem. So I don't have to do any derivation in class. I just tell them the two postulates of relativity. And of course, we can always show them some experimental data which made people understand that there is a breakdown of Newtonian physics, especially how the charged particle would move in magnetic field, and then the radius were not matching as the energy increased. But that's the motivation for doing the theory. So first thing we assume is that the time is not same. So if I send two signals at an interval of time t, the other observer will receive it at a time interval of k times t. That's where we have to wonder whether the time is same or not. That was the first challenge which was made to a Newtonian idea, and that's what is responsible for the theory of relativity. And with that, we are able to actually arrive at a Doppler factor. And from Doppler factor, we can easily come to the transformation equations. And then, of course, once we have transformation equations, we can expose them to all possible kind of calculations. What is the relativistic invariance? What happens to the length? What happens to the time interval? Now, this time interval and the Doppler factor are two different things. That also gets really cleared in their mind. And then, of course, we can lead them to velocity transformation, acceleration transformation. The space-time diagram also helps them understand the twin paradox, and that's why the power of this problem solving really works. I mean, I really don't have to teach students anything. It's just in form of a problem. I'm only supporting their learning while they solve the problem. The general relativity happens to be more complex ideas for people to understand. So instead of actually mathematically teaching them general relativity, I give them small problems. What happens in an elevator, accelerated elevator? What happens when it's falling? Then, of course, showing principle of equivalence in two different frames, one stationary in gravity and one in moving in free space with some same acceleration as g. And then how would the light beam travel in that? And then you establish principle of equivalence. Then introducing them to geometry of curved space. You know, one of the problem I have set is finding distance between 2 points on the same latitude and 2 points on the same longitude. And then they would understand what is the importance of greater circle and the geodesic, the shortest distance, etc. Uh, and then, of course, showing them what happens to the geometry on the curved surface as far as the area is concerned. For example, triangle on spherical surface will always have area which is smaller than on the plane surface. So those ideas would introduce them to curved space. Then we can introduce them to the idea of curved space-time. Uh, and it's very interesting. If you take 2 points, two particles which are falling in gravity, which are at the same distance from the center of Earth, separated by distance, then in their freely falling frame, they would come closer. Whereas if they are along the same radial line, then they would start moving apart, away from each other. Now that shows actually a curvature in space-time. So when you make students think about these things, then the ideas come very clearly to them. If you make them draw a trajectory of a projectile on space-time diagram, a normal projectile, then you can see this trajectory is curved, but if there was no gravity, it would be a straight line. So that's a curvature in space-time. So a problem actually allows you to illustrate so many things, but students come up with the answer. We are not ready-made providing them the answer. And then, of course, we can stretch it to GPS and so many things. Thank you very much. Actually, I would like to stop here because already told me that the time is up. So I would come to the last slide. Uh, uh, I have not listed the reference, but that's my email address. So anybody would contact me. I would be happy to share anything they want, which I have. Thank you very much. Thank you,
Okay,
Professor Srivastav.
okay. Thank you so much, sir, for a very nice lecture. And I must appreciate the way you explained designing instrument of physics learning using so many beautiful examples. Uh, so there is a question in the chat box from Dr. Partha Goswami. First question he has asked, what happened the triple point of water? And second is, water has second critical point. Where is the additional oddity located in
No,
the diagram?
I'm not going to answer physics questions. My purpose of this lecture was not to discuss physics. So we will keep physics aside. This was how to design an instruments of learning, a problem, or how to use problems for teaching as a model of
Yeah,
communication.
yes.
So I'm sorry if I'm not answering this question.
Okay, so second question is from Mr. Devendra Sharma. What formula we will apply in Excel for beats?
Oh, it's the same wave equation. You just choose the right parameter and you can plot the graphs. Same wave equation, sine omega t.
Okay, so there is no more question in the chat box. So let us thank our speaker. Thank you, sir.
Thank you very much.
Okay, now I hand over the session to Poonam ma'am.
Thank you, sir. It was indeed a vibrant lecture given by you on designing instrument of physics learning. The way you quoted the examples are beyond words. I'm falling short of words to explain falling short of words for you how you explain these things so simply. And if you can read, there are so many appreciation messages in the chat box. It was indeed a wonderful lecture, sir. Thank you so much. Now I request Dr. Shirish Pathare. He is from Homi Bhabha Center for Science Education, TIFR, Mumbai. He is going to give his views on the discovery based and inquiry driven undergraduate physics laboratories. I welcome you, sir.
Hello, am I audible?
Yes, sir, perfectly.
Okay, great. And I have hopefully 30 minutes. Let's see.
Yes, sir.
Okay, fine. Good afternoon to all. So I'll be for next, hopefully for 30 minutes or maybe less. I will try to discuss with you something which is very dear to me, the lab, the experiments in physics, and what it means by discovery-based or inquiry-driven undergraduate physics laboratories, and with certain examples, of course. Right. So, but before I go to that, NEP, the National Education Policy 2020, just has this sentence, which is quite nice. Pedagogy must evolve to make education more experiential, holistic, integrated, inquiry-driven, discovery-oriented, learner-centered, discussion-based, flexible, and of course, enjoyable. Of course, I'm not going to talk about all this, but mainly these two phrases, which I will be spending most of the time. When you talk about our laboratories or say traditional laboratories, and even you remember like your school days, and since you all are teachers now, remember now the present students college days also, that when they enter, the recipe of performing experiment is ready, and students, we expect that they follow that. Okay, they don't even dare to deviate from that. Okay, the choice of instruments, data collection techniques are spelled out in the recipe given. So of course, there is hardly any scope of deviating from that process. Students often find the time provided for performing that experiment very less, We all know, I mean, some of them still struggle to take the data set, even maybe 2 hours or over, or say 3 hours or over. And getting a repeat mark on the rough journal is considered normal, and then the reasons for it are not discussed. Which is like for any student, I mean, it's fine. I mean, I got a repeat mark, so I will do it next time. I mean, but why I got repeat mark, we actually, as a student, we don't think about it. When you talk about discovery-based laboratories, students are given opportunities to develop the ability to search for answers to questions, plan, conduct, interpret, and present results. They are encouraged to use their physics knowledge to communicate, argument, and present conclusions. And one or more routes are taken by groups of students working towards the discovery of a specific relationship or concept. Right? So that's basically the difference between traditional and, if you talk about discovery-based laboratories, these are some of the main differences that you can find. What are the advantages of such labs? Students take ownership of lab work. Right, so this is my experiment. I will work for it. I will try to find. I will try to investigate. Let me deal with the problems that I come up with. Right, instead of just depending on teachers and then this is not working, that is not working. No, so I will take ownership. Whatever is going wrong, let me try to understand and try to solve that problem. They gain better understanding of the processes of scientific inquiry because they do primary research. Of course, the moment you say that it's my experiment, okay, I have to solve the problems, this is kind of a small research that they conduct within those 2 hours or so. They learn lab skills that are difficult to incorporate into traditional scheduled laboratories. And of course, the main concern, inquiry-based labs that encourage experimentation can improve student performance and engagement without lowering exam scores. And this is like a report from Cornell University, a very recent report, which says that. But okay, fine. I mean, all these are very nice words. And as a teachers, you all must have learned all these things during your early days. So nothing great about it, what I told you. But the general impression is such fancy terminologies are impractical in regular practice. That's what we think. I mean, is it really possible to do all these things during our regular laboratory sessions in India? I don't know. Okay, let's see how we can do that. And there is some work which has already been done on how to do such things. And then these are the two words, procedural understanding, which will be come to our rescue. What do I mean by that? There's already a work done by my colleague Khapade and Professor Pradhan on procedural understanding. And there is this paper, one can enjoy this paper. What does it mean? It is referred to that understanding which is often implicit and goes behind planning and execution of experimental science in order to generate scientific knowledge from it. Okay, if you find that heavy, don't worry. In simple words, it is thinking behind doing, okay, or the decisions that have to be made for doing practical work. That means whatever that you do, I mean, why did I take this much of length for a simple pendulum? Why did I take only 20 oscillations and not 10 oscillations? Why did I not even take 50 oscillations, right? So every single step, okay, that you do in your practical work, if you ask this question, why am I doing that? Why, I mean, what is the logic behind doing this? That is what you mean by procedural understanding. Let me give you an example, right? So like when voltage is measured using an analog voltmeter, the range I'm using is 0 to 2 volts. Where the reading is shown by a pointer moving over a dial, the reading is constant, right? But when the same is measured by a digital voltmeter, range again 2 volts, the last digit is found to fluctuate, right? I mean, it's just not remaining steady, just not. I mean, I'm really troubled by that, okay? So when I'm doing that experiment, which meter should I perform or say prefer, right? And if you ask this question to any student, they will always say, I mean, use analog voltmeter, it's showing you a constant reading. But the whole purpose, of doing experimentation is that to understand the data that you are getting. How is your data? What is the quality of the data? The data that you are collecting, is it a stable one or is not stable one? Are there any fluctuations in that? What is the cause of that fluctuation? Can you really find that out? Can you try to nullify that fluctuation by doing certain arrangements? So that is the crux of doing experiment. Try to understand the system, right? And if that is the thing, then using digital voltmeter is more sensible, because that is showing you, that is making more visible what is the problem that is going on in your circuit, right? So when you talk about procedural understanding, such questions actually test students' understanding of choice of instrument, right? So if I have, say, certain number of instruments given to me, I mean, which one is more appropriate to be used, right? Let me give you some examples of some of the experiments. One will be bifilar pendulum and other will be black box type experiments. Bifilar pendulum is a very regular experiment in an undergraduate laboratory, so you will be surprised what am I going to talk about, right? The way in which it is presented, this is your, say, maybe some body. I have just taken a dumbbell. That dumbbell is suspended by 2 threads. These are the distances. So you have, say, 2d1. There is the distance between these 2 points, where the thread is suspended from the support. Then this is 2d2, where the this body is held by these threads, and then the thread length is L. The formula is given to the students directly. So T equal to 2 pi root of IL upon mg d1 d2, right? And then they are asked to find out the moment of inertia. That's your regular experiment. But the same experiment can be turned around and be presented in an investigative manner. How to do that? Just tell them that this is the relation, okay, general equation, T equal to 2 pi root of I by C, okay. Tell them C depends on mg, okay. So when you say C depends on mg, of course that mg appears in the denominator, so that hint is given to them. Now place remaining variables in the formula at appropriate places d1 d2 L by performing the experiment. So now you come up with the formula. You don't have to derive it theoretically. You have to come up with the formula experimentally. So how do you do that? So you suspend it, okay, and every time, as teachers, that whenever you do any experiment, try to focus only on 2 variables by keeping all other constant. So same thing they are expected to do. So keep d1 and L constant, vary d2 and measure T, right? So you vary this distance, okay, and measure time of oscillation. Plot natural log of T versus natural log of d2. You will get a beautiful straight line, okay. The slope is expected to give you minus 0.5. Now this is where fine, I mean, I have written here minus 0.5, but when you actually do the experiment, you don't get minus 0.5, but you might get minus 0.48 or maybe sometimes minus 0.54 or something. What students are supposed to do here is to calculate the uncertainty in the slope, okay, that how much slope can vary and whether 0.5 is within that limit or not. So they have to verify themselves and just have to tell them that it is going to be, if it's like fraction is 1 by 2, okay, this numerator and denominator are going to be some integers. So you just give them that hint, that's all. But then otherwise students have to come up with what is the slope, and then they have to interpret that it's going to be T is proportional to 1 by root of d2. Similarly, you do it for one more, okay. So you keep d2 and L constant, vary d1 and measure T. You will again get minus 0.5 as the slope, and you can relate that. So again d1 appears in the denominator under root, okay. And now there is one variable remaining. You don't have to do the experiment again, but you just do the dimension analysis, and then L will be in the denominator. So this is kind of a process which actually leads students to come up with the formula, right, and then decide how to collect the data, which graph to be plotted. Because suppose if you have 2 unknown variables x and y, and something it's like y is equal to x raised to n, and if you have to find out n, you have to take natural log on both the sides. This is what we have done, and n will be your slope of the graph. So this is kind of a process through which students actually goes, and at every step they have to justify why they have taken certain graph, what is the slope of the graph, whether it gives them the sizable values, that kind of thing. Black box kind of experiment, some of you might be aware of it, but these are some of the experiments. Like there are different types of black boxes: mechanical black box, electrical black box, or say magnetic black box. I'm going to discuss one of those black box now. So this black box is something which is hidden in that box, okay. That box can be of any shape. There's something hidden in the box, and you have to try to guess what is there inside with your existing knowledge of physics, right? So of course you are not supposed to open that box. But without opening, with existing knowledge of physics, you do certain measurements, do some graph plotting, and come up with what is hidden in that box. One such box that I'm going to discuss with you is magnetic black box, right? So you have this aluminum tube, okay? I mean, it just looks black, I mean, but you can take it of any color. But then in that tube, you have magnets and spacers, right? So this is a neodymium magnet. This is 1 centimeter by 1 centimeter. Its length is 1 centimeter and dia is 1 centimeter. Similarly, you have acrylic spacer or any plastic spacer will do. Even this dimension is 1 centimeter length and 1 centimeter diameter. So there are number of magnets and spacer arrangement inside the black box. Let me give you the solution. Okay, so let me give you the solution first, and then we will discuss how to arrive at that solution. So, so this is the arrangement in the black box right now. Okay, so you have north south, a spacer here. Okay, so this is a repulsive mode. Again, say 2 magnets. Again north, then south, north, now. So now this is like you have repulsive, then attractive, and attractive. So 3 repulsive and 4 attractive, right? So this is the, I mean one can have different arrangements, no harm in that, but we thought of giving such kind of a combination to students. I mean, you can try n number of combinations in this. What next? Most of us might have come across this sensor. Otherwise, to measure magnetic field, what we use is a Gauss meter, right? A Gauss meter is an instrument which measures magnetic field, but of course, which is very costly. And if we can afford it, great. But if you can't afford it, this is a sensor which is available in the market. This is WH315 linear Hall effect sensor. It's a 3-pin IC. And then what you do is you give 5 volts to this VCC and between VCC and ground, and collect output between this V0 and ground. Okay, so when there is no magnetic field, it gives you a typical voltage of around 2.6 volts. And then when you bring any magnet nearer to that, then you will either have increase in that voltage, or depending on the other polarity, you will have decrease in the voltage. As you know, it's a Hall effect, right? So if you have one pole of the magnet approaching that surface, you will have increase in the voltage. If you have other pole approaching that, it will have decrease in the voltage, right? So this is a typical sensor that you see here. Don't even, this is nothing. I mean, this is just a fancy look of that. So this is an acrylic strip on which I have certain connectors, which actually goes to 5 volts. So I'm using a power bank for supplying 5 volts, and this goes to multimeter. And this is my sensor over here. Now, what I'm going to do with this, I'm going to study the variation in the magnetic field of the magnetic black box. And how am I going to do that? This is the way I'm going to do that, right? So I have this as my magnetic black box, and then this is my sensor. So this sensor is going to move like this, okay, or along the length, okay. So in this direction. So starting from one end to the other end, right? So I'm going to scan the magnetic field variation as seen by my Hall effect sensor, and then I'm going to plot it. How does that look like? This is the thing, okay. Now this is some kind of a graph that you have got, but you have to take all those data very religiously, plot it very religiously, and then try to interpret. How will you interpret that? I mean, from this graph, you can't make out anything, let me tell you. I mean, you just look at this graph and absolutely no clue that you will get. But then you give 4 identical magnets to the students and 1 spacer. Okay, so you separately give these things to them. Okay, and then 1 tube, so they can insert those magnets and that spacer in certain combination and form a combination of that, a small combination of that black box. Okay, which students right now are not aware. I mean, whether it's repulsive mode or attractive mode. This experiment can be given as a project for the students and let them do this for the whole day, okay, or maybe a week or so, and then come up with the combination that they might have observed in the actual black box. Or you can guide them. You can guide them that right now, let's save some time and then try only 2 combinations. Let me show you. So the first combination will be south-north. So this is attractive, then a spacer, and south-north, right? So if I have this combination, the kind of graph that I see is like this, right? And now since I know the dimensions of the magnets and spacers, okay, this is 1 centimeter, 1, 1, 1, 1. I can match this dimension with the graph that I have got, and I can see that at this north-south junction, I'm getting one peak here. This north-south junction, I'm getting one peak here, and I'm getting a valley at the central point where there is a spacer, right? For repulsive, what I'm getting here is that at this north-south, as you have seen, north-south, you are getting a peak. So north-south, you are getting a peak here. South-north, you are getting a valley over here now, okay? And at the center, you are getting 0 over here, right? So this is the kind of graphs that you observe. What will you do next? Try to match that, okay? Try to match this graph, the patterns that you have got with the actual graph that you have got, and then you can come up with this combination. So this is basically what you have got here, as that this is the 0 over here. So south-south, okay, north-north again, then south-south, 0. Now you have north-south, so you have got a valley here. And so you go on comparing the graphs that you have got by scanning these two combinations. So now in this, if you really look at this experiment, it is something that makes students, believe in their data, because I mean, most of the data that they get in most of their practicals are either straight line or some very simple curve or something. But now this is some kind of a variation that they are getting, which they have to believe, right? And just keep on taking that data and then plot that data very well. Okay, draw a very nice smooth curve, and then decide on themselves like how this small combination that I have tried are matching with the actual magnetic black box data, right? So this is a kind of a, so all the black box experiments, even say electrical black box or say any other mechanical black box, checks their patience first thing. After patience, checks their honesty of what data that they are getting. So keep belief in the data that you get, okay, and then come up with a kind of a procedure. Okay, how will you go about doing things? You know, how if you believe your data, and then if you can convert that data into a graph, believe in your graphs, and then come up with the answer. So this whole discovery method brings about a confidence in them, brings about some kind of a develop some kind of a lab skills in them, and that's something that I think we all are aiming our students to do. So in conclusion, NEP 2020 explicitly wants to introduce the discovery-based culture, right? I mean, that's very clear. The picture is still unclear about the manner in which it will be incorporated in the present education system. How will it be, told through a syllabus? Okay, that this is how things will be. But the message is loud and clear. We need to change the way laboratories are conducted. The traditional the way of laboratory is not acceptable anymore. So you have to introduce something that will make students think. Okay, because when you get your students at vivas, of course you must have experienced this kind of a fear in their mind that, oh my god, I mean, why he or she is not answering. Okay, so that fear, okay, when students actually, if they discuss all such problems during the lab, if they take ownership, of course all those things will be disappear, and we can see a different picture altogether. So let me leave you with a quote, a beautiful quote. In theory, there is no difference between theory and practice, but in practice there is. I think. Thank you. Thanks a lot.
Okay, I think this is simply an excellent lecture given by you, sir. Thank you so much for giving very nice information on discovery-based and inquiry-driven undergraduate physics laboratories with the help of so many examples. And it's really very nice.
Thank you.
So I have not seen any question in the chat box. So I think everything is clear to the participants.
Yeah.
So let us thank our speaker.
Thank you. I think I have finished a bit early, but I guess the next speakers will say some good things about me that I have given some time. No. So thanks a lot. Thank you.
Okay, okay. Thank you so much, sir. Now over to Poonam ma'am.
Thank you, Yogesh sir. One thing I want to quote, in the month of November, me and Dr. Yogesh has attended a workshop, that is the NIUS Teachers Development Workshop. and there I met Professor Shirish Pathare,
Oh,
and we are privileged to have a lecture from him there as well.
oh,
So this is another opportunity to hear you, sir, and I am overwhelmed. You
Thank
have quoted so many examples, so many things so well, and the participants are also writing ki you have cleared the discovery oriented learner centers lab, and you have given so many nice explanation. That is something, very wonderful session. Thanks a lot, sir.
thank you. Thank you. Thanks.
Now, this was the last invited talk for today's session. Now, I would like to invite our paper presenters. They are waiting from so long to present their views. So, our first paper presenter is Miss Mohini Nagpal. She is from SSLT Gujarat Senior Secondary School, Delhi. She is going to speak on the topic New Dimensions of Assessing Students' Learning in Physics. I welcome you, ma'am.
Thanks a lot, ma'am. Share screen, I think.
Ma'am, I can't see you. Yeah, now you are visible.
Is my screen visible, ma'am?
Yes, kindly go to the presentation mode.
I think I'm in the presentation mode.
Now it is fine. Thank you so much.
Good afternoon, everyone, and thanks a lot for giving me an opportunity to speak at the 8th convocation. I am Mohini Nagpal, PGT Physics, SSLT Gujarat Senior Secondary School, and I'm going to speak on the topic New Dimensions of Assessing Students' Learning in Physics. First, I'm going to talk about what is assessing or what is assessment. We are like during this corona pandemic period, we are so much used to teaching and all that. We are stuffing the students with all the knowledge, PDFs, material, online classes and all that. But is actual learning really taking place? We cannot surely say about that until we know that we assess our students' knowledge. And national education policy clearly portrays about the fact that assessment is an important component, and that too formative assessment. National education policy clearly stresses upon the formative assessment aspect, and I'm going to talk about that only. The word dimension I'm going to talk about is basically the technological aspect. The national education policy also clearly mentions that technology as a tool can be used in a better way, not only for teaching, but also can be used a good tool for assessment also. So I'm going to talk about various assessment tools which are available, which we can use for making our students become critical thinkers. That is also one of the main objective of goal of our national education policy. So first of all, I'm going to talk about one of the web tool which I'm myself using with my like Mentimeter. Mentimeter is like a type of a presentation tool. Like we have PowerPoint presentation, in Mentimeter we have presentation slides, and we can post our questions in the form of different slides. Like for example, this is a question and it is formed in a like MCQ type, and there are 4 options, and students can post their answers. And there are 2 modes in Mentimeter. Like we have a like we have a teacher presenter mode and a student presenter mode too. I can be the presenter of my Mentimeter quiz, and I can shift the slides, and I can pause the slides. I can do any damn thing because I'm going to be the presenter. And there's a leather board. A leather board basically shows that these are the name of the students and these are their points. Students are being evaluated by the Mentimeter itself, and they are being given points, and the fastest student has got the highest point. And it basically evaluates. Students really enjoyed working on Mentimeter, and they feel like they're playing a game. And when we incorporate a gaming attitude to our learning, I think that's the best thing we can ever do. Then second web tool I'm going to talk about is mega exams. Mega exams, like we had our previous tool, which is Mentimeter. Mentimeter also we can have frame different form of questions. Similarly, in mega exams also we can form different forms of question. Just a teacher has to make a domain name. Like I have a domain name work physics, and using the domain name I'm going to add all the students of my class. going to add their email IDs. I'm also going to add their phone numbers. And then I'm going to create tests. I'm going to create as many tests as I want. And then I'm going to publish those tests. And there is also a student leaderboard here. And I can see how much each student has responded, and what is the average performance of my class, what is the average performance of the top bottom of my class. Everything I'm going to know. What is the average performance in a particular test. This is also a page from a mega exams only, screenshot from mega exams only, and we can clearly see that, for example, a particular student has got 5 marks out of 7 in a particular test. The time taken by that student was 10 minutes, and what was the average performance in that test, what was the average time taken. And using all these time taken aspects, I can plan my future test. What is the time interval I'm going to give it to them, how much time I'm going to limit it to them, what was the difficulty level. All these things I can make. The next web tool I'm going to talk about is Google Forms. Google Forms we have used many a times for gathering and collecting information, collecting data. But Google Forms can also be used for assessing students' knowledge and how much they have learned. For example, these two are two questions and they are MCQ based. They have been made, and using Google Forms they have been made. And using Google Forms we can make our questions into we can make a quiz type test also. Like this is an 8-point test, and 30 students here. 30 means that 30 students have responded to this test. And I can also see how many students and what was their score. I can see their individual performances. I can also see the range of the marks they have got. I can also see how many, most of the students have got 6 marks, no one has got the full marks, and no one has got 3 marks also. So I can analyze all this data, and this data analysis is equally important. And I can also analyze the individual performances of the children, and then I can guide them and give them appropriate feedback, because with assessment there comes feedback also, which is equally important. Then I'm going to talk about another type of tool, which is mind map. Mind map is basically a mind map making tool. Mind maps are basically in short, in one page you're going to present the whole picture of a particular topic. For example, using mind map, there is a mind map being made on the topic Coulomb's law, and this can be used as a tool for teaching as well as can be used as a tool for assessment. I can ask the students to make a mind map on a particular topic, and they can come with different kind of mind maps. They can use mind map online tool for making mind maps. They can make a mind map on paper also. They can use all different types of other tools are also available for making mind maps. So they can make and main mind maps using other tools too. Then we have another type of tool, blogging, which is a collaborative type of tool. Why collaborative type of tools are so important during this time when we are teaching children online. They are online, they are their respective homes. They can't see each other, they can't collaborate with each other, and collaborative activity is equally important, because until we collaborate with each other, until one student collaborates with the other student, the student will not be able to learn from each other. And when they will not be able to learn from each other, then proper learning will not take place. So there is a WordPress site which can be used for blogging. There is blogger.com that can also be used for blogging. And for example, there is a blogging type of activity site, like a student can post a question and then different student can put their responses on that question. In this way, one student can learn from each other, as well as a teacher can analyze and assess students' understanding of a particular topic related to this activity. Even if we don't want to use another tool for blogging, we can also do in Google Classrooms. There is a question mode. We can use that question mode and can put our questions here, or the students can also put their questions here, and then students can reply to each other, and we can just go on ask. And then a teacher can ask the students, and students can put their responses and viewpoints on that particular then comes a different category of assessment tools, which are Flipgrid and Powtoons. These are video-based assessment tools. Powtoons are just like PowerPoint presentations, but they are more graphics and animation involved, so students love doing them. We can ask them to make a PowerToon or a PowerPoint presentation on any topic, and they can make those presentations and then give it to us and then submit to us, and then we can see them and we can mark them. We can assess their knowledge of, and we can also ask 2-3 students. We can also make it a collaborative activity, and we can ask 2-3 students to work on a particular PowerPoint presentation. That can be done using Google Drive. We can the students can share the presentation with each other, and then they can work on one presentation at a time. Then we have Flipgrid. Flipgrid is also a video presentation tool, but it's a bit different. Flipgrid just works as a blogging tool works. Like in blogging, we have a question posted and people post and students post their responses. In a similar manner, in Flipgrid, what happens is a question or a video is posted and we post video responses to that particular question. So basically that is a video based assessment tool, Flipgrid. Then we are going to come to audio based assessment tool. Audacity is one example of that. Audacity is an audio based assessment tool, and audio based assessment tool works like just like video based assessment tool have videos where we post our videos. In audio based assessment tool, we post the students post basically audio messages related to a particular topic in hand. Now the question comes is how these video and audio based assessment tools can be used in physics. These are basically a seeming type of a communication type of tools which can be used in communication, like in languages, for assessing students in languages. But actually these video and audio based assessment tools can be used in assessing their practical knowledge. For example, we can ask the students to do some practical activity using the material available at home and then make a video of it, and then they can post the video. Similarly, this audio based assessment tool like Audacity, they can see the sine wave, they can see the waveforms of different noises like our noise or like a ball rolling down, and they can see the waveform, and they can also study sound, they can study wave formation, standing waves, and all that can also be studied using this tool. So it's not like that this tool is communication based tool. This tool can be used as a practical based tool, which we have to understand. Then is like FET simulations. FET simulations have become a very, very important way of teaching students. We use FET simulation of teaching our class for a particular. But we can also use FET simulations not only as a tool for teaching, but also as a tool for assessing students' knowledge. For example, we can show them any FET simulation of any topic, and then we can ask questions related to that FET simulation, why this thing is happening or why this thing is not happening. Can you explain this? And they can post their descriptive answers. So simulation can also be used a very good tool because they will be able to see the things they generally see in the word answers. They are able to see the things on their own, which will be a very good tool. So after discussing all those tools, I want to highlight another important aspect, which is framing questions. Like we generally, when we frame questions, we deal upon two models, remembering and understanding, or at most we deal about application level, and we don't go on to higher levels of framing question. But we should, as a teacher, it's our task that we should frame our questions in a different manner. We should not just use the remembering and the understanding levels for framing our questions. We should go on to higher levels also, like application, analyzing, evaluation, and creating, and then we can evaluate our students better. For example, like if I talk about Coulomb's law, then if I ask my students what is Coulomb's law, then they are going to say then it comes to remembering or the understanding level. But if I ask them that calculate the distance between two charges, if I am giving the force or I'm asking them to calculate the force, then I'm going to application level. But if I want to go on to other levels, then I can change my question into the form, suppose there are two charges, and if I move one charge nearby to the other charge, then are the both charges going to experience the same force, or the force is going to change? So as I'm going to change my question framing in a different sense, I am going to move on to other higher levels of the Bloom's taxonomy.
Excuse me, Miss Mohini. You have another 2 minutes to wind up.
I have already winded up.
Okay, thank you so much.
Welcome.
Okay, so I think this is something new ways to assess student learning in physics, and this is really a very beautiful lecture. There is no question in the chat box. Yeah, there is one question in the chat box by Mr. Rinku Das. In mind map available in mobile?
Mind map, like when we have opened that application in our laptops, we can surely open our that same application in our phones also. But how easy it would be to make those graphs using our phone, that's a big question. But that can be done. That's not so difficult.
Okay, so let us thank our speaker as there is no more questions.
Thank you, sir.
Thank you. Now over to Poonam ma'am.
Thank you, sir. Miss Mohini, indeed it was very good presentation. In this pandemic situation, I must say, the way you have show us the audio and videos based apps are really wonderful to use. So I expect others also kindly go through these apps so that we can have more exposure. Thank you so much, Miss Mohini. Now, this is my honor to introduce my teacher, mentor, and the one because of her, I am here in front of all of you, Dr. Pushpa Bindal, the Associate Professor of Kalandi College, University of Delhi. Welcome, ma'am. Ma'am is going to speak on the topic Curriculum for Multifaceted Development.
Thank you so much, Poonam. It's such a warm gesture. I am obliged. So, let me share my screen first.
Please, ma'am.
Yeah, just a minute. Oh. Yeah.
Ma'am, the screen is visible. Kindly go to the presentation mode.
Yeah.
Yeah, thank you.
Is it okay? Is it okay?
Yes, ma'am.
Yeah.
It's fine.
I first of all, at the outset, I would like to thank Professor Ved Srivastava and IAPT RC1 for giving me this opportunity to express my views on this topic. So the topic that I've chosen to talk about is the curriculum for multifaceted development in context of National Education Policy 2020. So this is a work done by myself and Dr. Transa Srivastava, and we are both from Department of Physics, Kalindi College. So, because so many eminent speakers have already talked and they have presented their views, they have contributed significantly to this convention, 8th convention by IAPT. So it is, I think, necessary to talk about few of the highlights of National Education Policy 2020. NEP 2020 aims for a holistic, multidisciplinary, and futuristic education. It wants to change the face of education in India. So far, we have always been saying that I am a science student or I am a science teacher, or similarly, the students keep on saying I am a humanities student. So the NEP 2020 basically wants us to break down this boundary and aims for no separation between arts, humanities, and sciences. It also wants to do away with vocational or academic streams. Everything basically, goes hand in hand. It is aimed by the government that the gross enrollment ratio in higher education, and that includes the vocational education, it must reach 50% by 2035 from the current, not so current, it was the 2018 data, from to 26.3%. There is going to be a lot of emphasis on quality research and equitable use of technology. It is actually the need of the hour, and whatever we design now has to be oriented towards that. It basically talks about doing away with rote learning. This is a very important point. You see, so in today's scenario, rote learning is just mug it up and then throw it back. Okay, so whatever is taught, maybe you are not able to understand, but you can still do very well in exams by reproducing whatever is taught to you, or whatever is you have learned, whatever you have mugged up. Okay, a very good example, it has just come to my mind. It was shown in the movie Three Idiots, where the guy, although he's supposed to be topper of the college, and he, speaks something absolutely without understanding and becomes, he's himself is humiliated and he humiliates the head of the institution as well. So this should actually be done away with. It the NEP 2020, it aims for inquiry-based project-led ecosystem of education. The student must become prone to, must become one with, posing questions, posing inquiries, inquiring themselves, and they must be able to understand in a, kind of doing with things, doing things rather than, just mugging up or doing derivations. It has to be project-based. It is also, basically proposed, or actually it is going to be manifested, that the undergraduate degree program can be 3-year or 4-year duration, depending on the choice of the student, and it can have multiple exit points. And also the students won't lose even if they decide to come out of it at the end of 1 year, 2 years, 3 years, or 4 years. There will be different outcomes, and the student is going to gain only, not going to lose. Now, because there is a lot of flexibility which we are talking about at undergraduate level, so master's courses also cannot be stereotyped. We will have to go for master's courses of different designs based on what student has learned at undergraduate level, because now the undergraduate level itself is so flexible. You are going to have flexibility in curriculum, you're going to have flexibility in assessment. So master's courses will also have to be redesigned. By 2020, single stream higher educational institutes, they are aimed to be phased out, and we aim at harmonizing together higher educational institutes into large multidisciplinary universities, colleges, and clusters of knowledge and basically education hubs. Overall, we aim for a more experiential, holistic, integrated, inquiry-driven, discovery-oriented, learner-centered, discussion-based, flexible, and of course, the most important point, enjoyable education. If we don't enjoy it, we don't do it thoroughly. What is the vision of NEP 2020 towards curriculum? Number one, we aim for a flexible curriculum. If that is not so, then there is no change possible. We are talking about creative combination of subjects. A physics student can learn music or history or pol science, and vice versa. We are going to focus more on key concepts and ideas. We are going to encourage critical thinking and analysis-based learning. And in order to achieve all of it, or at least a fraction of it, it is extremely important to reduce course curriculum content to its core essential. Now, what is it that we are proposing? We are proposing few changes in the curriculum, or at least some points which could be talked about, which could be discussed by the relevant committees. And actually this will be applicable to not only physics but any other subject. Now, for a major, if a student majorly wants to study physics, then you could have physics as a major subject, or if some other student studying another subject and major, say history student or mathematics student, if they also want to study physics partially, then physics can be a minor discipline for them. So, first of all, let us talk about the major discipline. For a major discipline at undergraduate level, 60% of the curriculum should be treated as core papers, and that should include laboratory work. And we can always have minor project works associated with each paper. This is a must, because if you make everything mandatory, then there is no room for flexibility. So we can have 60% as basically major subjects, major core papers, because it is important to teach some of the basic concepts mandatorily to the student. So everything cannot be flexible. So at least 60% should be core according to us. Then within each paper, 70% of the curriculum should be mandatorily taught. Now, what I mean to say is that if you want flexibility, if you want to introduce flexibility, then everything in the curriculum cannot be taught. Then it is a very, very tough race to just complete the curriculum and teach whatever is expected of student to know in the examinations. So what I think is that 70% should be necessarily taught because core papers, that knowledge has to be given to the students. And from particularly we are talking about universities where one person may be teaching and absolutely, some different person may be setting up the question papers. So some basic guideline has to be followed by everyone. So it is important that some portion should be necessarily taught, and what we can do is that based on the concepts taught, some portion of the curriculum could be given for self-study, and we could always as teachers evaluate through assignments that portion. So it is not that we are kind of depriving students of knowing something, but we are trying to develop a parallel method of teaching everything, and yet leaving room for the flexibility. Now 30% of the paper, it must necessarily be assigned to problem solving techniques. Those who are a part of Delhi University, they are familiar with this, that almost all papers, they have been teams. I myself was convener of one of them. So we have developed basically problem solving papers, problem solving problem sets. Okay. And they are very, very important, because if we just teach theory, the students don't learn how to apply that to daily life problems. So we have all developed and we have put in a lot of work for that to develop, basically develop problem sets and kind of model question papers. So that 30%, when do we have the time to complete that? When do we have time to make the student familiar with those concepts, the problem solving techniques? So that is possible only if the 30% of the workload hours are necessarily assigned for this problem solving technique. And we can always have minor projects like giving the problems where the student is able to think, something on his own. And maybe this can be part of the internal assessment. Now, all core papers, I think, should be finished in first and second year, because the student is relatively new to the undergraduate level, and whatever is necessarily to be taught by the teachers, that should be dealt with at the first and second year level. Third year needs to be devoted to choice-based papers, and the department must float a substantial number of papers which have to be resource-based, right?
Excuse me, ma'am.
Yes, Puna?
Ma'am, you have another 2 minutes.
Oh, okay, I'll try to complete as soon as possible in just 2 minutes.
Yeah, thank you, ma'am.
Yeah. So there is one major problem which I'm sure people know about. Our students, they have to study necessarily maths and chemistry, physics students, as their minor paper. Why? Because they are told, they are counseled by us only, that if you don't take them, then you can't do MSc physics, and you can't go for school teaching. They are inherently embedded into the system. So we have to do away with these conditions. Only then the student who wants to study music, history, economics, along with physics, will be free to do that. And it will also be, helpful for those students who are preparing for IAS, etc., competitive exams. So they can choose their paper. But for that, the changes have to be made at master's level also, and at the recruitment conditions for school teaching also. Okay. And I also say that those who want physics as a minor subject, they should be taught some basic papers which must include all basic information on physics. Particularly, I vote for inclusion of alternative sources of energy, because that is the need of the hour. And it should also include a lab course which should include basic experiments on mechanics, optics, and electricity, because they are relatively easier papers, easier disciplines of physics. Okay. And of course they must have, they are needed to complete a certain credit score for getting their degree. And we must review the curriculum time to time. It should not be that okay, I'll just quickly go through the challenges, because the curriculum is supposed to be fluid. It will be a very heavy challenge to implement it. Actual workload calculation and an appointment of required teachers, that will also be a tough job. And we need exceptional professors who are not only good at their own subject, they're also interested in others. Then only we can talk about minors and majors disciplines. So overall, we have proposed few incorporation in designing physics curriculum, and that could be applied to other papers also. These are some of the references that we have, basically consulted. And I would like to thank everyone for listening. And thank you.
So, ma'am, you have highlighted the development of curriculum in the purview of National Education Policy 2020 very well. Thank you so much, ma'am, for your marvelous lecture.
Thank you, Yogesh. Thank you so
Yeah,
much.
ma'am, there is one question in the chat box.
Yes.
What when teachers do not justify the students?
See, I would say this is a question of integrity. If a student, if a teacher is sincere, then the teacher doesn't need to be told.
Yes, yes.
And the teacher will take all pains, will go out of the way to, basically teach in every possible way. Every possible, including the mentoring also. But if the teacher is, if there is a lack on integrity, I'm sorry, it will be difficult to, address this problem.
Yeah.
It has to, we have to work on ourselves.
Yes, yes.
Yes.
So let us thank our speaker. So over to Poonam ma'am.
Thank you, sir. Thank you so much, ma'am. I'm always honored to hear from you in college time and every time whenever you speak. It's really my honor.
Thank you,
ma'am.
Poonam. Thank you, my beloved friend, little friend, my student, my daughter, anything.
Thank you, ma'am. Thank you for the honor. Yeah.
Yes.
And our next speaker is Dr. Triranjita Srivastav. She is an assistant professor at Kalandi College, University of Delhi. She is going to speak on 4-year undergraduate course, Fluidity and Merits. Welcome, Dr. Triranjita.
Thank you, Poonam ma'am. Am I audible?
Yes, yes, perfectly audible.
Okay, should I share the screen?
Yeah, please.
Okay, thank you. Uh, Good afternoon, everyone. Myself, Dr. Triranjita Srivastav from Kalindi College. I would like to thank IARCT team for giving this opportunity to speak about the 4-year undergraduate course. Actually, this work is carried out by me and Dr. Pushpa Bindal. So the topic of the presentation is 4-year undergraduate course, Fluidity and Merits. In this talk, I will briefly discuss few major recommendations of NEP 2020 for undergraduate degree program, followed by a case study of undergraduate degree pattern being offered by University of Delhi. The major recommendation of NEP 2020 is, first of all, it promotes holistic and multidisciplinary education system, like the traditional education system being obeyed long back in Gurukul, Takshila, and Nalanda. The arts, humanities, and science courses will be on equal footing. That is, any student can simultaneously choose a paper, any paper like art paper, along with any science paper. The next recommendation is that it will boost vocational and practical skills, which will directly lead to better job opportunities. Another important recommendation is the formation of academic bank of credit. It is like an academic repository of credit points being earned by the student while pursuing any degree. Now comes the major change in undergraduate education system is 3 or 4-year undergraduate program. So a student has a flexibility in pursuing undergraduate degree with multiple entry and exit options. These recommendations also include enhanced research opportunities. Now I present a comparative study of undergraduate courses, the conventional undergraduate courses, as compared to the NEP recommendation. So if we see the aspects, the exit options, so before NEP, like at present, there is no such exit option. A student has only option either to successfully complete the degree or exit without any benefit like certification. But after this NEP recommendation, if a student pursues a 3-year or a 4-year degree program, Then in 3-year degree, it has two options, two exit options, that is after first year and second year. So these are the additional exit points. Similarly, for 4-year degree program, it will have 3 additional exit points, that is after first year, second year, and third year. So what does it mean? What will it lead to? Now, what will be the pattern of the degree which will be awarded to the student? Like at present, after successfully completing the 3-year course, a student gets a bachelor degree. But after NEP recommendation is successfully implemented, then if a student exits after first year, then they will get a certificate. If they complete 2 years, then they will get a diploma. If they complete a 3-year, then bachelor's degree. And if they complete the entire 4-year degree, that is after fourth year, they will get a degree which will be known as bachelor degree with research. Now, what about the entry options? Like at present, the student has no such option. If anyone exits the undergraduate program, there is no such opportunity to rejoin the program. But according to NEP 2020, despite of exit without completing the full duration, a student may re-enter from where they had left off at the same or in different institution. So there is no such compulsion that a student has to rejoin from the same institution. They can even rejoin from other institution as well. So NEP 2020 is a boon for a student, as many of the students, they keep on changing their mind about the career, and sometimes due to certain unavoidable circumstances, they have to, or they may have to drop their education to support their family or something like that. So they have a flexibility that they can rejoin the course anytime they want. Then, as I discussed, this leads to a holistic development, because it will lead to the overall development of an individual. This will also, we believe that it will lead to a low dropout rate. And as we discussed, it will give enhanced research opportunity. Now, as a case study, if we see the courses offered by University of Delhi, then in 2013, University of Delhi offered a 4-year undergraduate program, that is FYUP. This course structure offered discipline-specific courses, some applied courses, which provided hands-on session and practical knowledge, and along with a dissertation, that is a research work. So this was a small step towards the NEP recommendation. But somehow this FYUP course was rolled back in 2014, because this was something, a new recommendation, new course, that is an undergraduate course will be of a 4-year. And there was no uniformity in the in different universities or different institutions, that all the undergraduate programs will be of 3-year or 4-year. So this was something like a new concept, where the undergraduate program was becoming to be 4-year. So it was not well accepted by people, and it was rolled back. Now, at present, since 2016, a 3-year undergraduate program, which is known as CBCS, is offered by University of Delhi. So this course structure has core courses, discipline-specific courses, ability enhancement courses, which is to enhance their communication skills. Then there are skill enhancement courses, which are basically lead to certain applied courses and along with hands-on session. Then there are generic courses. These generic courses are interdisciplinary. Actually, these courses are the courses which a student has to take apart from his own department. That will be from some other department. So at present, I mean, since 3 years, I am seeing that a student of English honors, Hindi honors, and journalism and other streams also, basically the arts streams, the students are opting for physics as a generic course. So physics is becoming popular among the students, and moreover, the physics honors students, they also go for arts courses by opting different generic courses. This course structure has a research work, that is, a student has a flexibility that if they want, they can opt for dissertation. So this is also a step towards NEP, which is a recommendation, and probably we believe that from next year it will come into existence. Since each coin has two sides, so apart from the benefits, there are several challenges also. Like, the first challenge is to develop a harmony between science and art courses in a form of interdisciplinary course, and to achieve a fixed workload, to develop an infrastructure for multidisciplinary courses. So in summary, we discussed the major recommendations of NEP 2020 for 3 and 4 year undergraduate course. We discussed the comparison between the conventional undergraduate course and the NEP recommendations, and discussed a case study of FYUP and 3-year CBCS undergraduate course being offered by University of Delhi. So I would like to summarize my talk with this quote, that is, multiple entry exit options and the academic credit bank will give students lot of flexibility in getting educated and earning degrees while they are working. We are moving towards the concept of build your own degree. These are few references, and thank you.
Okay, Dr. Triranjita, you have showcased very well the entry and exit option before NEP 2020, during and after NEP 2020. Also, you have discussed 3 and 4 year undergraduate program as per this policy. It was indeed really a very nice presentation. So thank you so much.
Thank you, sir. Thank you.
There is no question in the chat box, so let us thank our speaker.
Thank you.
So now I call Poonam ma'am.
Thank you, sir. Congratulations, Dr. Triranjita, for such a wonderful talk. You have emphasis on all the points which are really needed for the NEP 2020. Thank you.
Thank you, ma'am.
Now, our next paper presenter needs no introduction. She is a very hardworking and a well-known member of our team. But for the new participant, I want to introduce her. She is Dr. Seema Vats. She is an assistant professor at Motilal Nehru College, University of Delhi. She is going to present her views on the innovative way of measuring fall of potential across potentiometer wire using ultrasonic sensor. Welcome you, ma'am. Ma'am, you are on mute. Kindly unmute yourself. Ma'am, you are on mute.
Can you hear me now?
Yes, ma'am. It's fine now.
Thanks, Poonam, for such a nice introduction. I'm very thankful to Professor V.P. Srivastava and whole team of IIPT for giving me this opportunity to present my talk. I am also thankful to Professor H.K. Shezwani, under whose supervision I have done this work. So let me share the screen and just present my work. Can you see the screen, Poonam?
It is not visible right now.
Just a second. Just a second.
Be ready. Seema.
Just a second. It's saying a host disabled participant. It's saying
now,
host disabled participants.
Kindly check right now.
Just a second. I'll just
Yeah, sure. No problem, ma'am.
Yeah, now it's visible. Just a second. Yeah.
Yes, ma'am. Okay. Yes, ma'am. Kindly go to the presentation mode.
Fine.
Yeah. Thank you, ma'am.
Thanks a lot, Mona. It's an innovative way of measuring change in potential across potentiometer wire using ultrasonic sensor. This work has been done under supervision of Professor H.K. Shezwani. So basically, the aim is clear. Now, the apparatus we use here is potentiometer wire, Arduino Uno hardware, ultrasonic sensor, laptop, or a PC, and an L-shaped wooden board and aluminum foil. This is our Arduino board that we use, and here you can see there are different number of pins, that is 5 volts ground. These are analog pins A0, A1, A2, and these are the digital pins, and this is the cable where we connect it through PC, and here we can place different sensors and all the pins are being provided. So actually, what is Arduino and what it can do? Arduino is an open source electronics platform for engineers and non-engineers. It is based on easy to use hardware and software. And it can do various things, like its hardware can actually read inputs such as light on a sensor, button status, it can detect motions. And these are the different things that can be done with the Arduino hardware. But however, I'll limit my presentation to the experiments of physics. So this is actually the picture of the apparatus that we have used. This is an ultrasonic sensor. We can see there are 4 pins available over here. This is a cable which connects PC to Arduino. This is an aluminum foil. We actually wrap it up and place it under the wooden board. And this wooden board, it is then placed on a potentiometer wire through a copper cable. This is being showcased in this diagram. So basically, this is an Arduino board. And this is a potentiometer. This is a wire. The one end of the wire is connected to the 5 volts pin of Arduino board. Another end of the potentiometer is being connected to the ground of the Arduino board. And then this is the L-shaped wooden board, which act as an obstacle. Underneath this, there is a copper wire and which is wrapped in aluminum foil. And this is being connected to the analog pin of an Arduino board. And ultrasonic pens, the sensor is again connected to the Arduino board. So the thing is that what is the significance of this experiment and what we are doing this? Actually, we all our distinguished speakers have talked about this physics being integrated with low cost effective technology. So we have actually took the basic principle of physics and it is integrated with low cost effective technology of Arduino Uno. Then there is a sensor based real time measurement. We actually measure the things, and this will be demonstrated by Shezwani sir later on. It is now a project and analysis based learning, and it is enhanced by this experiment as we have in this national education policy. This is a need of an hour. And also we can create an innovation by designing other experiments, because like we have designed this experiment using ultrasonic sensor and obstacle, we can design other experiments, or our students, like they can now detect the cracks in metals by using both the things. So this is basically a task-based assessment skill. It can be used in that format. It enhances practical and applied components in the curriculum. So this is a flow chart of a procedure that is being followed. First, you just make connections. Let's see what the connections are. You connect the potentiometer end to 5 volt and another end to the ground of the Arduino board. Connect the wire with one end wrapped in aluminum foil, paste it on the bottom of L-shaped wooden board, and the second end to the A0 analog pin. Connect the ultrasonic sensor to 4 pins. They are on the Arduino board. That is a ground, that is VCC, trigger, and echo. So after we do the connection, we write down a program in Arduino file on PC. So this is a software part of Arduino. We verify the program, and then after being verified, there are no mistakes, we upload it on the Arduino board through a cable. So what actually then happens is that the ultrasonic sensor, it triggers high frequency pulse of short duration, and echo is being received by echo sensor. This time interval of to and fro path measured by ultrasonic device gives us the length. Potential at different points is read at analog pin A0, and readings of the potential versus length is tabulated in PC. What is now the working principle behind this experiment? Actually, when an electric pulse of high voltage, that is 5 volt, is applied to ultrasonic transducer, it vibrates and it generates ultrasonic waves. These waves strike an obstacle. Here we have a L-shaped wooden board, and the ultrasound waves are reflected back in the form of echo. This generates an electric pulse. Sensor actually calculates the time taken between sending sound waves and receiving the echo. Here we know that ultrasonic detection, it introduces very high frequency sound waves. Actually, the range of the sound waves goes from 100 kilohertz to 50 megahertz. Then the distance of the obstacle is related to the velocity of sound waves in the medium through which waves are passed and the time taken for echo reception. Hence, the distance is being calculated. Arduino Uno helps to read the voltage at a point where obstacle is placed on the potentiometer. It can be seen from the results that the potential falls as the length or distance increases. Note here one point, that here we measure the potential at a point and not the potential difference. We have to calculate the potential difference once we get the set of readings with the starting point as a reference potential 0. This will be discussed later on in our slides. This is basically a long program of Arduino that we have based on the principle of ultrasonic sensor and all. Here we can use the velocity of the sign. This is the formula being used, and here this voltage that we study, it is being divided 5 divided by 1024, and therefore it is actually increasing the accuracy. So I will not go into the details of Arduino program right now, and I'll just directly move on to the results. So basically, these are the results that we get. This is a time step. That is the time at which we have our wooden board is placed, and the echo this ultrasonic sensor send the waves. This is a potential at a point. So all of you can see the data. We have a potential is 3.93, 3.90, 70. This is decreasing as the distance between the ultrasonic sensor and the obstacle increases. So this is a set of reading. This is a real-time measurement which is done, which will be demonstrated later on. So what we do, we take these length and the potential as a reference point, and then we subtract the first reading from the second reading from the first one, and similarly we get this thing. So what do we observe? We observe that as the length increases, the potential difference increases. L being changed, it's a independent variable here. So we are taking it on x-axis, and then we have the potential difference on the y-axis. We have the points being scattered, and actually they are like a straight line. We have not done the fit as such, but we have just tried to show that it is varies linearly. For the information, we have again plotted the potential difference on the x-axis, and then we interchanged length, and again we got the same thing. So basically, the results is about that as the distance between the ultrasonic sensor and the obstacle increases, there is a fall in potential. The difference in length is directly proportional to the potential difference. Now, one thing is to be noticed is that the time interval is measured in microsecond. So we can actually measure the distance and length up to 0.001 centimeter. And using an analog pin A0, potential can be measured up to 0.005. The one beautiful thing about Arduino is that this experiment has been repeated thrice, and we get the same set of readings. Students can be made aware of all these things during the experiment. So now the thing is that what is actually the learning from the experiment? Here, the students can also be given task of devising another experiment, which has been harped by many of our speakers, that it should be a task-based assessment. So once we demonstrate things, there can be number of experiments that can be devised from this same principle of physics. For example, one of this I have tabulated, the ultrasonic waves can detect cracks in the metal, because in metals, ultrasonic waves, they just travel very nicely. But if there is a crack, so there is a change in medium, they will be reflected back, and we can actually go and detect it. So this is the students learn the nature of propagation of ultrasonic waves in different medium, and they use this concept in detecting various parameters like potential, finding cracks, etc. So we have actually used the technology to take readings using software and hardware to do the experiment, and which is the need of the hour. So now the demonstration of the experiment will be given by Professor H.K. Sejwani. Over to you, sir.
Sir, you are on mute.
Am I audible now?
Yes, yes, sir. You're audible, sir.
Okay. Before I show my experiment.
Excuse me, sir.
Okay.
I think you are using two devices. That's why there is an
Yes.
echo. So kindly
Yes.
disconnect one device.
I'm using two devices.
So may
And video for the second device is not been allowed by you. And you will have to allow it because I want to show the experiment.
Okay.
So I am currently on the laptop, but I will have to show my experiment with the help of my mobile. So
Sir, I
therefore,
have done. I have given you the permission, but sir, just mute one of the device voice.
yes, I am just
Yeah.
muting it.
Yeah. Yeah, please, sir.
Instead of muting, I have made the volume almost zero.
Yes, sir. Now it is fine. And I have given you the rights for both the devices, sir.
Yes. Before I show my experiment, I would like to thank Dr. V.P. Srivastava and the team which has worked so hard to organize this workshop. I would also like to thank Dr. O.P. Sharma, during whose tenure of the presidentship I started presenting various experiments. मैं अपने गुरु प्रोफेसर के.सी. ठाकुर का भी चरण स्पर्श करना चाहूँगा, जिनकी वजह से मैंने मोटिवेशन लेकर इन एक्सपेरिमेंट्स को करना शुरू कर दिया था। 5-6 साल से मैं हर साल एक नया एक्सपेरिमेंट प्रेजेंट करता हूँ और आज मैं आपको दिखाने वाला हूँ जो सीमा बस जी ने आपको कनेक्शन वगैरह दिखाए हैं, उस एक्सपेरिमेंट को मैं शो करूँगा, जिसमें हम आपको पोटेंशियल मेज़र करना और लेंथ को मेज़र करना विद द हेल्प ऑफ द आर्डिनो और उनको रिकॉर्ड करना, ऑटोमेटिकली रिकॉर्ड करना बताएंगे. So I am just showing you the various components that we are using. You can just see that this is our ultrasonic device. There is one trigger and one is echo. Trigger only sends the waves, and then it is reflected from this particular device, from this device. You can see that in this device, there is an aluminum foil here, which is at the edge of this vertical board. This vertical board is now put on this potentiometer wire, which you can see that this is the potentiometer wire. One end of this potentiometer wire is connected to the ground, and another end of the potentiometer wire is connected to the 5-volt with the help of the Arduino. This Arduino device you can see this the red wire is connected to 5-volt, and black wire is connected to ground. That means there is a potential difference of 5 volts. Now, while taking the reading, what we shall be doing is that we shall be moving this L-shaped. Yes. नहीं दिख रहा है? हेलो, मैं चेक करता हूँ. यहाँ पर तो मुझे चल रहा है. Are you able to see?
Yes, sir, I can see on the second window. On your second device, I can see the table, the L-shaped structure you have placed, black and red
So
wire with the
it is
Arduino
visible,
device.
it is
Yeah, yeah.
visible, na?
Yes,
Okay,
sir, I
that is
can
what I
see.
will
Yes,
see.
sir.
So what we shall be doing is, what I shall be doing is, I shall be moving this device on this potentiometer wire, and at every point we will be getting the value of the potential as well as the length. Length will be given to us by ultrasonic, and potential will be measured by this particular wire, which is connected to A0. So we will be measuring the potential as well as the distance. So I will show you how the automatic recording of this is being done, and that I will do by sharing my screen. I am just now sharing my screen. Uh, okay. Yes. Can you see my screen? Can you see my screen?
Yes, sir, screen is visible,
Okay. So
but
now you
there are
can
so
see
many
that there
windows
is
open.
a software which is called as a Terraterm, and I am just clicking it, and you will see that when I say connect the serial port, my Arduino board is connected to the port COM5 of my device. Now I say yes, and then you see that there are readings coming on the screen. So after every some interval of the time, readings will be changing, and for every change reading, I'll be say this will be recorded with the help of my logging. So I log my file, and give it some name. Say I am giving it mmm dot csv. The CSV is a special Excel sheet file with the help of which we are able to get this. And then I'm taking this timestamp also. I'm using the timestamp also, and then the save it. So now what you will see is that readings will be coming, and for every reading I'll be moving my L type of the box, and then another reading will come. As soon as another reading comes, I move my box, okay, and then another reading comes. I move my box. Yes, now reading has come. I have moved my L-shaped device. Actually, what is happening is whatever you are seeing on this, it is being automatically recorded in a CSV file, for which the graphs was shown by Simawas. I'm just now closing this device and show you that there are readings on my. So you just the file that I made was mmm. This is .csv. When I click it, you will find out that whatever the readings were there, those readings are appearing here. This is the timestamp, the time at which the reading was taken, and then I started from here. I started from this particular point when I started decreasing the distance, increasing the distance, and increasing the potential difference. So I just delete it, yeah, and then I can plot the graph. This is the potential, and this is the distance. You can see as the distance is increasing, the potential is decreasing. That means there is a fall of potential with the increase in the distance. Okay. Now the reference point, this has to be taken. Reference point, this has to be taken, and already Seema was had already shown you. So I'm not saving it. And closing this file, and the other files that we other readings that we have taken. Seema has shown one reading, and I'm showing you two other readings also. This is the reading that we have taken, and corresponding graph has been plotted with the help of the Excel itself. See, this is the file abc2, and I had given it name abc2.csv, and then I converted into the Excel sheet. This is, and you can see the graph between the potential difference in volts and the length in this. This is because potential difference is making a first column, and L is showing the next column. Therefore, the length is coming on the y-axis and the potential is coming along the x-axis. These observations, you can see that there is a expected line is this dotted line, and the variations are there, very minor variations are there of these points on the above side and on the lower side of this. So that means the automatic recording can be done, automatic in the Excel sheet, and we need not plot the graphs with the help of manually. We can get this graph automatically with the help of the Excel sheet. Excel sheet is one of the very excellent software which is available everywhere, and we can always plot the graph. The students can be made to understand how the readings are taken automatically. We have also made experiments. Seema Vas, Swati Chawla and myself have developed in the last 3-4 months large number of the experiments, with the help of which we are able to detect the time interval, calculate the value of the G by different methods using the IR sensors, using the LDR sensors, etc., etc. But that is a different thing. The important thing is that experiments can be done automatically. The readings can be taken automatically. They can be recorded automatically, and this is a great help to the students to perform the experiment in a different way in the laboratories. Normally, we are not performing the experiment in the different way. That is why the students get bored in the laboratory. They are performing the same experiment for the last 20 years or last 30 years. But then different way of performing the experiment is the crux of this. Particularly what is there in this experiment? In this experiment, you know that we are basically making you understand the principle being used for the comparison of the EMF of the two cells. You use the E1 by E2 by taking a null point. E1 is equal to KL1, E2 is equal to KL2, and therefore E1 over E2 is equal to the L1 over L2. But why E is equal to KL1? The basic principle is the fall of the potential across the potentiometer wire, and that is what we are doing, and that is what is not there in our syllabus. Okay? These type of the things which help the students in the development of the innovative methods. The other experiments, of course, could be shown, but now since we are concentrating on this graph, the important thing is that we should always learn different ways of doing the things, and then making the students interested in the performance of the experiments. Thank you very much. Thanks a lot.
Excuse me, sir. Sir, I request you if you can kindly show the experimental setup once again.
Hello.
Yes, sir. Sir, is it
Am I
possible?
audible?
Yeah.
My experiment is over.
No, I'm saying, can you please show the experimental setup once again?
Sure.
Yeah, please, sir.
Is it visible?
Yes, sir. Can we have a close look?
Yes, this is ultrasonic. This is ultrasonic device. Are you able to see the ultrasonic device?
Yes, sir. Yes, sir. It's clearly visible.
It is clear. And behind this, there is a Arduino board.
Yes, sir.
Arduino board is visible.
Yes, sir.
This red wire is connected to the 5 volts, and the black wire is connected to the ground, and this wire is connected to A0. And then there is a board. There is a potentiometer wire, and I can move this mobile to the end of this. So this is one end. Simply a board, simply a wooden board, and one wire connected on this. One end of the wire is connected to this particular point. Another end of the wire is connected to this particular point. This point is given 5 volts. This point is given 0 volt. So there is a fall of potential. There is a fall of potential from this point to this point. Okay,
Thank you, sir.
and this one is acting like a jockey. But if we use jockey, then we shall not be able to measure the potential, the distance. Something must come in the way of the ultrasonic, so that ultrasonic wave strikes this, goes back, and the time interval is measured. This time interval is measured in microseconds. Since it is measured in the microsecond, therefore, even if you move it by 1 millimeter only, there will be a variation in the time. And therefore, accurate measurement of the distance can be done with the help of this. And also the potential in the Arduino, whatever potential is, say 5 volt potential difference we are applying, in the Arduino, it is divided by 1024. It is a 10-bit microprocessor, and therefore 10 bit means 2 raised to the power 10, and 2 raised to the power 10 means 1024, 2 raised to the power 10. So 5 volts is being divided by 1024, which I take approximately equal to 1000. Therefore, what we are getting is 5 divided by 0.005 volts we can measure with the help of this. So accuracy of the measurement of the potential and accuracy of the measurement of the distance is very much there. Okay? And therefore, our graph is, you can see in our graph, almost all the points are along the straight line.
Okay.
You want to see more?
Thank you,
Should I
sir.
show you
Thank you.
again?
Yeah, no, it is absolutely
Okay,
fine.
thank you.
So it is really an innovative way to measure the fall of potential using Arduino software, and very well nicely demonstrated by Sejwani sir. And thank you, ma'am and sir, to share this new innovative idea. Also, let us thank our speaker. Now over to Poonam ma'am.
Yeah. Thank you, sir. Thank you, Seema ma'am. Thank you, Sejwani sir. This is really another kind of experience in online mode. We can have a pleasure to have, a live example which we can see on the screen. That's why the participants are also very curious to see the setup. They keep on writing in the chat box, the setup is not visible, setup is not visible.
I would like to inform you
Yes,
that I
sir.
have developed, with the help of my team, Seema Vas and Swati Chawla, 20 experiments of the physics. It's
Great,
not only
sir.
one experiment, it is we have developed 20 experiments of the physics, and whenever we shall be getting any opportunity to show it live, I'll be happy, and we as a group will be happy to show it.
Yes, sir. Thank you so much. We are
Great, sir,
privileged
great.
to have you here. Thank
Great.
you, sir.
Thank you, Single Sir.
Yes, sir. And a lot of appreciation you can also read in the chat box. See, like, this is an innovative way, nice idea, good work. Thank you, sir. Thank you, ma'am, for presenting. Now, our next paper presenter, actually, I am privileged to introduce such a senior and knowledgeable faculty, Dr. Partha Goswami. He is an associate professor at Deshbandhu College, University of Delhi. He has deep knowledge of various subjects, but today he is going to speak on a topic, a heuristic approach to Fermi statistics with few non-interactive fermions in one-dimensional potential. I welcome you, sir.
Thank you. Am I audible?
Yes, sir, you are perfectly audible.
Okay, so thanks everybody. Uh, this work actually is the inspiration behind the work, and a part of it was done by Dr. Yogesh himself, and the remaining part was done by me. So the aim is the following.
Should I share the PDF, sir?
Sure.
Yeah.
Please do. Please do.
Is it visible?
Yeah, visible. Yeah. The aim is to present an extendable example of do-it-yourself approach on the theory front. Because ultimately, I feel, and almost everybody here feels, that that is the ultimate way to learn. And, and this is the ultimate way we can make students enjoy the process of learning. So we go to the next slide, that is where we have stated the problem clearly and formulation of the problem. Please go to the next slide. I titled it as an exercise in inductive pedagogy because in our classroom, we have been following deductive method. On the other hand, inductive method is very powerful. I feel so. But inductive method needs a very different orientation, particularly from the faculty front. This is an example which probably fits the description. We are giving students a data set to analyze, and we want students to obtain some more information. The approach entirely is heuristic. What is what is heuristic? What does heuristic approach mean? It means it involves guesswork. It involves approximation, educated guess, all kinds of things. Sometimes intuition. Intuition also gives sometimes a lot of valuable information. So, of course, Fermi statistics, Bohr statistics, anionic statistics, all fractional statistics could be taught in an usual way by deductive method. So here to our, say, for example, our undergraduate students, I pose this problem of Fermi statistics in the following fashion. We have n non-interacting electrons, and they are to be accommodated in quantum states of one-dimensional quantum harmonic potential, quantum harmonic oscillator potential well. Fictitious, because in one dimension, I don't think in solid state we have example of three-dimensional potential well, for example, in 3-5 semiconductors, gallium arsenide or AlGas, etc. But then three-dimensional quantum harmonic oscillator potential will be a very complicated example. So I have chosen a fictitious toy example of one-dimensional quantum harmonic potential. And according to the Pauli exclusion principle, each electronic state, which will be characterized by two quantum numbers, n and ms, where n, the quantum number n, describes the orbital psi n x is the position variable in one dimension, space variable, and ms describes the projection of the spin momentum on a quantization axis, and it can be occupied. So the electronic state can be occupied by at most one electron. The spin is equal, spin quantum number, of course, is s equal half. So there are two s plus 1, two possible states with spin quantum number ms equal plus minus half.
Should I change
so
the slide?
each orbital, yeah.
Should I change the slide?
No.
Okay.
Let it be there. So each orbital is labeled by, therefore, quantum number n, which can accommodate two electrons, one with spin up and one with spin down. Now please change the slide. So at 0 Kelvin, let Nf denote the highest filled energy level, where we have started filling the levels from the bottom, say n equals 0, because this is a quantum harmonic oscillator. And continue feeling higher energy levels with electrons until all n electrons are accommodated. It is slightly convenient if n is an even number. The condition 2nf equal capital N will determine nf. This is value of n for the uppermost field level. The energy of the highest occupied level, as we all know, is called Fermi energy, denoted by EF. So for one-dimensional system of electrons, the chemical potential at 0 Kelvin is equal Fermi energy will be 2 times H cross omega Nf plus half. We all know that this is how the harmonic oscillator, this is what the eigenvalue of quantum harmonic oscillators are. So this will be our Fermi energy. And we also know that probability, all this information, initial information should be imparted to the student. Otherwise, the student wouldn't know what to do with the given data. So these are not much, I feel so, not very heavy information for undergraduate students, say at the third year honors level or third year honors level. So probability of occupying a state at energy E at 0 Kelvin is Heaviside step function. We all know that. Theta mu minus E. Where mu is the chemical potential of the fermion number, which is just like a step. As we know, I don't need to draw the graph. We all know how does a step function look like. Now I give a data set to obtain graphical representation at t equals 0 Kelvin. This is actually the heart of the problem. So please go to the fourth slide. Please go to the fourth slide.
Yes, sir, we are on fourth slide.
Here, since we are on QHO, quantum harmonic oscillator, energy levels must be equispaced. And I take them as 5 milli-electron volt, 15 milli-electron volt, 25 milli-electron volt, 35 milli-electron volt, and so on. And I just randomly put the occupation at lower energy level, 5, 15, 25, you have occupation as 2, occupation number as 2. But as we go to the higher level, higher energy level, we have either 0 or 1, but never greater than 2, which is it ought to be due to Pauli exclusion principle. And milli-electron volt, of course, will correspond to roughly 100 terahertz frequency. We can always calculate this. So this oscillator, this imaginary oscillator of ours are oscillating at roughly 100 terahertz frequency. So our levels correspond to one-dimensional quantum harmonic oscillator. The probability is given on the last column. Last column, probability of occupation is calculated like I have for lower levels, probability 1, 1, 1. For 4 levels, 4 or 5 levels, I have probability 1. And subsequently, I have fractions, proper fractions. We all know probability is a non-negative proper fraction. So now this information, now something has to be done from student side. This you have given. So I give the student an information that the estimate Fermi energy. And I give them the information that at Fermi energy, probability is half, which we all know from our expression for occupation number at energy equal Fermi energy, probability of occupation is half at 0 Kelvin. So student, as shown, in the fifth slide, please go to the fifth slide.
Yes, sir. Yeah, on field.
So I had pointed it out. Probability is 0.5, and that corresponds to the energy in milli-electron volt equal roughly 95 MeV, because this is energy in electron volt multiplied by 10 to the power minus 2. So Fermi energy will be roughly 95, 90 MeV. So this way a student will be able to get what Fermi energy is for this fictitious set of data. But student, after all, is learning something. And the graph is presented, graph of energy versus corresponding probability. Obviously, this is not a step function. Step function would have been something like up to 9.5 or 95 MeV. Probability is 1, and then all of a sudden dropping to 0. That would have been the step function for or the graph for 0 Kelvin. However, this is not so. Naturally, the distribution corresponds to some higher temperature, not 0 Kelvin. So using the distribution formula, one can easily calculate, just a small numerical calculation which student can do, easily calculate and find that the corresponding temperature, take any reading, for example, at let us say 120 MeV, probability, corresponding probability is roughly 0.2. So I have the Fermi occupation number formula I put in out there. At non-zero temperature, I get the temperature, which roughly comes out to be 300 Kelvin. So I do many such calculations, and I find mean temperature roughly around 300 Kelvin. So I have thus made student, without introducing complications of the statistics, I have made students aware of what Fermi energy is and what should the distribution, probability distribution look like at 0 Kelvin or at finite temperature. Now, the next slide, please go. Please go to the next slide.
Yeah.
Seventh.
Yes.
Seventh. Okay. So once we have, is it sixth? Oh, sixth.
Yeah, it's a sixth slide, sir.
Sixth. So I have written down temperature estimated is Boltzmann constant times temperature is 0.02498 electron volt. It can be estimated from the graph, and T is thus nearly 300 Kelvin. So graphical representation below corresponds to this toy graphical representation. I have generated data on my own, fictitious data, but of course I have kept Pauli exclusion principle, etc., which fermions obey, in mind and presented to the student. And I found that the student have been able to evaluate and show that, okay, this distribution should correspond to a temperature 300 Kelvin. So I do not stop this. I do not stop at this. I have now Fermi energy or chemical potential. I have temperature. I have now the entire formulation of thermodynamics to get the thermodynamics of this one-dimensional quantum harmonic oscillator. For example, partition function, those who are familiar with statistical mechanics, I am sure everybody is here. So we can calculate partition function with the formula. Seventh slide, please. Seventh, last. Yeah. So we can calculate partition function. Partition function once calculated, will give me Helmholtz free energy. This thermodynamic potential is very important. It is a function of n number of particles. N, by the way, could be obtained by sigma I GI Fi. GI is the number of states in ith level, and Fi is the probability of occupation of the ith level. So NVT, Helmholtz free energy, is function of number of particles, volume, and temperature. So F is easily calculated. I've not shown any calculation part. In fact, I have shown a graph of partition function versus temperature, which shows that partition function shoots up as the temperature rises. And first derivative of thermodynamic potential will give me the entropy. This is del F del T at constant N and V. Of course, here everything N and V not explicitly present. So temperature derivative of Helmholtz free energy will give me entropy. Further, I can calculate, I have not calculated, but I just wanted to show that the entire thermodynamics could be calculated now. Like specific heat will be T ds dt. T ds dt will be S being df dt. So specific heat will be T times second derivative of free energy. So that could, by simple differentiation for one-dimensional oscillator, it could be calculated. And I have shown here a graph of entropy versus temperature, which also shows upward trend, which means my calculation, whatever I am doing, is not unphysical, because entropy has to increase as temperature, as a function of temperature. So what did I achieve by giving this example? I feel that I have achieved the task of giving the student a flavor of how thermodynamics of a system, I have taken simplest system, could be calculated, and how statistical mechanics is connected with, which is description at microscopic level, and how that is connected with thermodynamics, which is a macroscopic description of the matter. So what I feel is not big examples are needed to show these concepts. Even a simplest of all, a one-dimensional quantum harmonic oscillator, and if at all, if one wants to be more realistic, one can take one-dimensional anharmonic quantum oscillator, where maybe a quartic term will be the perturbation. And if you want to give students a flavor of perturbation theory, you can calculate the perturbation and corresponding change in the energy eigenvalue, and of course, corresponding change in the energy eigenvectors as well. So right at the beginning, I said the example is extendable in the sense that from QHO, quantum harmonic oscillator, you can choose quantum anharmonic oscillator as your system and show the same thing on one front, that is on quantum mechanics front. On the statistical mechanics front, as we all know, the Bose and Fermi statistics, they are not the end of the world. There is something in between, anionic statistics, fractional statistics, which of course gets applied to in the fractional quantum Hall effect and all so on. So all such statistics like Holland, U statistics, and all such statistics could be given, well, through properly tailored example, we can give in this way flavor of all such statistics. And I'm sure even an undergraduate student would be able to understand. I think this presentation is a step towards deductive teaching and learning, which is all that is required for if we want our country to be independent in, let's say, 50 years' time on basic sciences as well as technology front. Thank you.
Yes, sir, I want to add one point here that using this problem, the student can easily calculate or find out or compute the thermodynamic other variable also, like speed of light, viscosity, and
Yeah, definitely.
yes, they're many
Definitely.
variable they can easily calculate using this Helmholtz tree.
No, I can
Find a
go a step
problem.
further. I can go a step further, Yogesh. They can calculate even the quantities like, say, conductivity, etc.
Magnetization.
Conductivity, magnetization, if
Yeah.
we introduce magnetic field. So,
Yes,
lot
yes.
of possibility is there.
Yes, yes. Okay.
Thank you so much, Partha sir and Yogesh sir, for such an informative, valuable, and wonderful approach. Study of behavior of fermions is really very interesting. There is no question I can see in the chat box except the appreciations. Sir, you have put the joint work so aptly. So let's thanks our speakers. Thank you so much, sir. Since we are through with all the talks of day 2 of our annual convention, now time to say bye or thanks to everyone. So now I would like to request Dr. Seema Wirtz, the EC member, IAPT RC1, to propose vote of thanks. Over to you, ma'am.
Thank you, Poonam. Can you hear me?
Yes, ma'am, you are audible.
Okay, thanks so much. Honorable Chief Guest Professor Roop Manjari Ghosh, BC Shivnadar University, respected Professor Ajoy Ghatak, Meghnad Saha Professor Nasi, our most valued invited guests and distinguished speakers, all the paper presenters and the participants. It's my proud privilege to have been asked by Professor VP Srivastava, our respected president, to propose the vote of thanks on this 8th annual convention IAPTRC1 in the context of role of physics education in National Education Policy 2020. I take this opportunity to express my profound gratitude and sincere thanks to Professor Roop Manjari Ghosh for accepting our invitation and gracing the occasion with her esteemed presence. Thanks a lot, ma'am, for your encouraging words and sagacious advice and the guidance. I express my gratitude to Professor Ajay Ghatak for his esteemed presence throughout the session and for presiding over the session. I would also like to acknowledge my gratitude to Delhi Science Teachers Forum for their enormous cooperation in the organization of this event. I'm very much thankful to Dr. N.K. Sehgal, Professor Gagan Gupta for gracing this occasion with their esteemed presence. I, on behalf of the whole team of IAPTRC1, convey my heartfelt thanks to all the distinguished speakers who are revered personality in the academic sphere for accepting our invitation and spare time to share their valuable thoughts. The erudite presentation by Professor K.P. Ramesh, ISC Bangalore, Dr. Pratibha Jolly, ex-principal Miranda House, Professor Rajaram Nityanand, Ajit Premji University, Professor V.B. Bhatia and Sri R. Joshi from NCRT for setting a benchmark for a series of resourceful and illuminating discourses in this event. We are guided with sense of direction and food for thought by your excellent presentations. There are other very excellent presentation by Professor Vijay A. Singh, CE BS Mumbai, Samendra Pratap Singh, Shiv Nadar University, Dr. Atul Modi, VES College of Arts, Science and Commerce, Mumbai, and Dr. Shirish Rathore from Tiffer, Mumbai. Once again, I express my sincere thanks to all the distinguished speakers and invited guests for sharing their valuable thoughts. They will no doubt serve our college, schools, teachers, and universities in a good state as we enter into NEP 2020 era. We are deeply thankful to all our paper presenters, Dr. Amit Kumar, Dr. Poonam Jain, Dr. Ananya Banerjee, Dr. Yogesh Kumar, Dr. Punita Verma, Dr. Pushpa Bindal, Dr. Taranjita Shrivastava, Dr. Partha Goswami, and Professor H.K. Sezwani, who have shared their idea of the tools required to implement NEP 2020. An event like this cannot happen overnight. It requires planning and a bird's eye for details. We have been fortunate enough to be backed by a webinar technical team of very motivated and dedicated colleagues, Dr. R.K. Tiwari, Dr. M.S. Bhandari, Ms. Vandana Banga, Dr. S.K. Singhal, and Poonam Jain and Yogesh Kumar, who have worked day and night under the supervision of our esteemed President, Professor V.P. Srivastava, to organize this event. Our words may not be capable of communication and our sense of gratitude. My sincere thanks to Dr. O.P. Sharma, Dr. Ravi Bhattacharya, and Professor H.K. Sezwani for their guidance and support. We remain obliged to our whole team of IIPT RC1, Dr. Giri Bhardwaj, Professor K.C. Thakur, Dr. Rajiv Tyagi, Manoj Koshak, Ms. Ramnik Kapoor, Dr. Prem Singh, Dr. Manoj Tiwari, Dr. Vikas Mittal, Dr. Rakesh Kumar Bhardwaj, who are the backbone of this organization. Last but not the least, I express my sincere thanks to all the participants who spare their valuable time to be with us this whole afternoon. Thanks once again to all of you. Over to you, Poonam. Now you can just take over the session.
Thank you so much, ma'am, for proposing the vote of thanks. Before signing off formally, I welcome you, sir, Ajoy Ghatak, sir. He has joined us 30 minutes before. I have seen him, but since the sessions were going on and I don't want to disturb the paper presenters, so now I welcome you, sir, because you are always a pillar behind all the motivations. You are always a source of motivation for all of us. I once again thank all the speakers for enlightening our audience with their deep knowledge. Also, this event is not completed without mentioning a big thank you to our participants for making this annual convention a great success. Thank you, everyone. At the end, stay home, stay safe, and more on, stay connected.
Congratulations to all of you.
Thank you
That
so
is
much,
mine.
sir.
And
Thank you, sir.
you
Thank
have
you,
done
sir.
a wonderful job, really.
Thank you.
Beautiful.
Thank you,
And,
sir.
in India now, sometimes I feel there are just too many webinars. I have a webinar starting at 5 o'clock that I have to attend, then I have to give a talk. So sometimes I get a little overwhelmed, and I think the same is true for participants also. But it's a great contribution. The contribution that all of you are making towards the upliftment of education, and that is affecting the younger generation. Even the afternoon talk that Punita Verma and Pushpa Bindal are organizing, they have done a great job. They are doing a wonderful job for the benefit of the younger generation, and the role that you all are playing in uplifting the educational system, physics education. is extremely important. Yesterday, unfortunately, today morning, I was very busy with a personal thing and I could not attend. But yesterday's presentations were extremely good. And it gives us hope that things will be better in future. And I'm indeed very, very happy and proud of all of you. I'm probably the oldest person now in your audience. So I am really very proud and very happy. I don't want to prolong. Congratulations all.
Thank you,
Over
sir.
to you,
Thank you, sir.
Poonam.
Thank you, sir. Now I need permission from Professor VP Srivastava to end formally this meeting for all. Sir, may
Please,
I?
please. Yes, please.
Thank you, sir. I once again thank you, everyone.
Thank
A
you.
very good afternoon.
Enjoy the evening. Enjoy the Sunday evening.
Thank you, sir, and same to you.
Thank you, everyone.
Thank you, sir.